Well, hello there, everybody, and welcome to SkyTour Livestream tonight. As you can see, it's another beautiful comet night, and we're going to do our best to show it to you in the best of lights. It's looking stunning right now. I mean, it's just beautiful. Now, it is a lot further away, and it's going a lot more southward. Remember, it came up across the pole and then went south from the pole, so it's bringing up now into the constellation of, I believe it's in Auriga tonight, and it is actually in Auriga as I think about it. And you can see this beautiful green glow. You'll also notice there's a tail right here, right there. You can see that tail right there. That's the gas tail, the ion tail. So if you draw a line straight through that and keep going, technically you should come to the sun. But the trouble is, that tail could be into the page or out of the page, so you have to think about the 3D geometry of what you're looking at. And most likely the end of the tail at this end is much further away than the tail at this end, so it's actually pointing kind of like, like that, coming back toward us. So you don't really get to see that when it's seemingly projected on the sky like this. This is the dust tail, right? So it's already gone by us, and it's heading now away. As you can see, it looks smaller tonight than it has in the past. It was much bigger, filled the whole screen last time. And it looks very different than it did. But this is Comet 2022 E3 ZTF. The ZTF, as I've mentioned before, stands for Zwicky Transient Facility on top of Mount Palomar down in California, where I'm actually going to be there in a couple of weeks. In Pasadena, actually. The Zwicky Transient Facility Telescope is a robotic search that looks for things like this in the sky. And it, of course, found it. So it found this process, or this comet in the sky, and proceeded to log it for us. Let's first of all, I want to say hello to everybody that's here. I want to welcome all of you. Donald Kunzer was first, and he's asking about full screen versus other things. We'll talk about that in a minute. And Vera's here. Hi, Vera. Hi, Tara. Tara's with us. And who's this SkyTour livestream guy? Oh, that's me. And then, of course, Michael Hedrick is with us. Hey, Michael. How you doing? Fantasy's with us. And Cyclone is with us. And Ivan Hernandez Chavez, welcome. You're new around here. Nice to see you. We're looking at the comet, as you can see right there on the screen. Okay, we are looking at Comet C2022 E3 ZTF. I'm going back in the comments, so I recognize maybe I'm a little bit late to that. So, in any case, good to see you. Daisy and Zoe are now joining us. Nice. Sam S. is with us. Good to see you. C&D Boy is here. How are you? Yeah, so this is looking gorgeous tonight. And for those that are kind of new, let me just give you a little preview. That is to say, a bit of a look around the screen so you know what you're looking at. Over here on the left side, this right here, this is our telescope control section. This is our telescope computer right here that you see. This is the telescope out in the building, 2,500 miles from me right here. And this is, of course, me. Hi there. This is our stacking software right here. This, of course, is the main view. And this is the camera control cluster and our focus control section over here. And so that's something that's the basics. Now, many times we will actually get rid of everything and show you the full screen, right? We don't always do it, but we do sometimes do it. And when we do that, all right, it looks kind of like this, all right? And I'll move that over, move this out of the way here, put that down. All right, so then it'll look like this, So that's good. And it's just a stunning comet tonight. So that's beautiful. And I see Daryl is here. Let me give him a call and bring him on in. As you know, Daryl Mason in Colorado joins us nightly on our streams, and we shall bring him in right now. So once again, the comet is looking stunning tonight, and I will be we'll be noticing some other. We'll probably be seeing some other nebulae and stuff as we move farther up into Auriga. Maybe have to check and see where it's heading. And Daryl is with us. Hello, Daryl. How are you?
Hello, Mark. I'm fine, thank you. Hello, everybody. Sorry I'm late.
Well, dinner calls.
There was a contest between you and homemade chicken noodle soup.
Oh, I don't know. I don't know.
Guess who lost?
Yeah, I would not. We'd be starting later too if it was me.
Yeah,
That's good though.
Really,
yeah,
excellently well done.
Nice.
Pat myself on the back here. Sorry.
Excellent. You can. You're allowed.
Share your screen with me.
I will. Just a second.
Folks, you're going to hear one or two alarms going off in very short order. One is going to be a tea kettle whistling, and the other one is a buzzer in about 25 minutes after that.
All right. All right. So here's the comet now. It looks really pretty, Daryl, and I noticed the gas tail is right here, and it's remarkably blue. It's actually got a blue tint to it. See that?
Uh-huh.
Yeah. And I think that comes from the fact that the comet's a little further away, so the colors can be more saturated when that tail gets smaller in the area of the sky. When it's spread out, it's hard to see the color.
Tea kettle.
Gotcha. Go ahead and take care of it. All right. So. All right. And so yeah. So this is only a 25-second shot. We've actually stacked 23 frames here. And the comet's moving, so it's going to blur the comet a little bit, but we're going to save this just like you see it. And then we're going to save it just like exactly as you see it as well. And this will actually be really cool because you can then go get this on our server. Where do you find that server? At SkyTourLive.org. You scroll down to the next section, and you'll see Take Me to Cool Pictures. And then you can actually get these pictures from tonight, and it gives you instructions how to go in there and check it out. All right. Very nice. This is actually looking better than it has. Okay. Very nice indeed.
Okay, I'm back.
Alrighty.
Gonna hear a buzzer go off in about 20 minutes.
Alrighty.
So hi everybody, how y'all doing tonight?
That's it. Well, hey, they're all doing well, I think.
Good.
Yep.
I haven't had a chance to say hi to everybody yet. Boy, I was looking at windy.com. It was clear here and clear in Arizona, and
yeah,
it must have been psychic or something.
Yeah.
Mark messaged me about 60 seconds later.
That's it. Yeah. Well, here's what I'm going to do. I'm going to actually clear this because we're going to actually do a longer exposure here. So I'm going to try and get this gas tail. All right, you can see it faintly here. Now, let me see if we can pull it out with just a little processing. All right. The center is artificially bright because I'm not doing what's called a flat field. But there you can see the tail pretty brightly there. And we're going to do another look. Let me see if I can actually I'll bring in my flat, and we'll do that. So then we'll clear it, and we'll do a Izabela. Hi, Izabela.
She'll be right back.
I see that. No problem. Okay.
I bet it's your dog.
That little yapper. That's a cute dog. We're going to do a 50-second exposure here just to try and grab this tail. I'm going to increase the gain to 300. All right, and just so you know, again, I didn't point out the important things. Let me just point it out now. Okay, this right here is the important thing. This is the exposure over here that you see. And then we have this right here, which is the gain. This is the sensitivity on the sensor, the gain, and the exposure is how long we're going to expose it to that sensitivity. So we're going to do that and figure out, and then we'll figure out what we're gonna get. So we have to experiment a little. All right. So there we go. All right. So now let's go back and clear this, and we're almost ready with this 50-second exposure. So let's see what we got. We've got 1 second to go. All right, let's see now. We're gonna do this here. Okay, there's the tail. All right, and we'll color correct now, and that should make the tail actually a little bit better. There's the tail, that gas tail, that ion tail. All right, and this is the first frame. And as I said, this is going to be blurry because it's moving. And over the night, we'll see it move. Oh, yeah. And now the second frame, you'll notice it'll be much clearer. Let me just zoom in on this here if I can. Okay.
I'll ask you a favor in a minute.
Yeah, so now in about 6 seconds, 5 seconds, we're going to see this get a little bit better because a lot of this noise is going to go away and this will look more sharp. You ready? Okay, here we go. Watch. Okay, so now the tail, I know that may not have looked at, but look at how blue. You see the blue here? What?
Carry on, I'm listening.
No, you were laughing. I thought you were. What are you laughing at?
Well, it may not look any different, but it is. No, I see it.
Yeah.
I mean, it's nice and blue. Carry on.
Yeah. That's, you know. The reason it's blue, that's the ionization, the color of the glowing glowing electrons. Sorry, when the electrons bounce back into the atom, they're ionized, and you're looking at the ionized color. And different materials ionize a different color. Carbon, a diatomic or a molecule of carbon, you know, carbon connected to carbon, boom, zingo. That's a Starlink. That ionizes, the electrons fly off the molecule, and when they jump back into the molecule, they give off green light. All right. Same thing with cyanogen, which is another carbon compound with nitrogen, CN, and it ionizes as well and glows green because of the sun's light. And Marianne is here. Hello, Marianne. We have the whole SkyTour live stream startup nonprofit crew here. We have Tara here and we have Marianne. Hi, guys. So show them some love, because without them, none of this would be possible. That's a beautiful tail. Holy cow.
And some of you might recall last week or whenever we looked at the comet, the tail was pointing the other direction.
Oh, yes, it was. That's right. Exactly.
The whole comet's kind of done a flip-flop in the sky.
It has.
Mark, can you go to Stellarium for a minute?
I might be able to.
Please.
Let's go to Stellarium.
Hi, Cindy.
Cindy Murphy, hello. Let me take away the object ID here. We don't need that right now. Yeah, what do you want?
Can you get Capella and Mars in the same field of view? There's Capella.
Let me pull back here a little.
Okay,
There's
Capella.
Mars.
And last night you were there by one of the kids, weren't you? The three little stars in the triangle.
Yeah, we were there, and you see it's heading this way. It's heading out toward Mars. Let me just pull this back here.
It's just about halfway between Capella and Mars tonight.
Yeah, so it's heading toward Mars. It's going to actually be in the same field as Mars by February 10th, and that's just 3 days away. And it looks like it's going to be clear. And guess what? We'll probably stream it. Twist my arm.
Sure.
Right.
Can you go back to Capella for a second?
Yeah.
Show where you were last night.
Well, I could certainly do that in just a minute. What is this one? This is... I forget which function key that was. All right. Okay, there's Capella. That's where I was.
There's Capella, and you see the three stars just to the upper right of Capella. Well, Auriga, the constellation, is a charioteer. He's a famous guy driving a chariot. And the star Capella there is his left shoulder, and it's also, Capella is known as the goat star. It's an ancient star, an ancient constellation. Capella has been known for a long, long time as the goat star. And then you have those three little stars in that triangle right there to the upper right. They are called the kids, like baby goats, you know. And he's holding them in the crook of his left elbow. And there you go. And then the comet last night was right near that the upper of the two stars on the right side of the little triangle. Is that correct, Marc? Zeta, Auriga?
Actually, we were. Let me get out of this here. Let me just go back. We were up here. Let's go up here now. We were at Saklateni yesterday.
Okay.
Yep, and that's one of the kids. We have Hades, Saklateni, and Almaz.
Saklateni.
Yes.
Yeah, I remember that last night.
Yeah, it's
somebody actually misspelled Sadatoni or something like that.
Yeah, I think it was Saklatoni or Saklatani or something like that. Yeah.
All right, and you all got a cool picture of Saklatoni last night. It's a nice double star.
It is.
One's orange and one's blue.
Now, I didn't stream it, but it is up there on the database.
Okay, cool.
But you notice where the Flaming Star Nebula is relative to the comet tonight. Now, as we zip along toward Mars, we might be able to see hints of some nebulous detail in our images as we head toward Mars, which is over here. But tonight would be the night to do that, you know. And I'm seeing some hints over here. Let's go back for a minute.
Look at all that cool stuff there too. This is like driving through Beverly Hills.
It's just beautiful, yeah.
All right.
There's our beautiful dust tail. And look at the gas tail. The gas tail is really prominent, and it's even a bluish green like it should be. It's really blue, you know, it's a very blue.
I have a question for you.
Yeah.
Okay, we know the green is from nitrogen.
Yeah.
And comets often show a blue-green or almost cyan color.
Yes.
Hyakutake was famous for that, and Hale Bopp had a famous blue-green tail. What's the difference between the blue-green of whatever and the green of nitrogen?
Well, it's the same compounds. It's just the nature of how many of them get liberated to form the coma around the coma or this area around the expelled stuff. It's just the nature of how much of that is liberated. Comets are well known to have carbon-carbon molecules, and they're well known to have cyanogen molecules, which are the CN versus CC. So depending if that stuff is tightly bound to the surface and the sunlight doesn't do a whole lot to them, it depends on the age of the comet and how much of that stuff came off the last apparition, last time it was here.
Okay, but it is the same thing in both
the green is always the same. Yep.
And the gas, the ion tail.
Yes.
Marc, Izabela says my audio is soft, and I hear your music pretty loud.
Oh, well then maybe that's because of that little issue there. Okay. All right, we're covered now.
Does that sound better, folks?
Yeah, I actually had my speakers on. Sorry about that. So it was coming in through double. So, but thank you for that, Izabela.
Okay.
All right, so I'm gonna just save this right now, and then save it exactly as we see it. All right, this is 50 seconds.
One of the nitrogen compounds. Well, it's got CYAN on the front, and you know, cyan is one of the four colors in four-color printing.
Yeah.
Like on your, your computer printer. Does that do something to denote the difference in color between, like, the diatomic nitrogen and carbon? I'm sorry. The diatomic carbon and the cyanogen.
I think that the name cyan may have a history that relates to cyanogen, and so it's possible, but I'm not really sure of the history of the naming. And that's probably something that's a Wikipedia lookup, and who knows, it might even be right. You know, Wikipedia is not often right. But
yeah, I could do that.
yeah, try that out. See what you get.
Very good. Carry on.
I'm gonna try and give us just a little pumping up of this. This plasma tail here. Plasma tail is very obvious here. Okay, and let's see if we can darken it up, add some contrast. There we go, look at that. Now we can see this beautiful plasma tail. Wow. Now let's zoom out to the full frame here. That's about it right there. That's the full frame. Look at that. Ah, nice. This is good music for this too.
Okay, cyanogen is it's a cyanide compound.
Yes.
And it is colorless and toxic, of course. Cyan, the color, a greenish blue color, used in photography and color printing of one of the primary colors. And cyanide is known for the blue or the green, I think. Let me look.
It is. I mean, remember, the cyanogen molecule, when ionized, upon recombination of the electrons with the molecule, you get green light given off, right? Because they absorb energy to leave the atom, and then they give off energy when they go back into the atoms, and they give off light when they do that. Same as hydrogen giving off red light.
Mm-hmm.
Now they drop to different levels, but the primary level is going to be the one that makes the greenish light.
Okay. Must be cyanide.
Yeah. And of course that led.
It does seem noticeably bluer tonight.
Yeah, the tail. The tail is actually showing very well. Now I also redid what are called the flat frames, and the flat frames are ways to get rid of the differential glow of different parts of the sensor. So that might make the colors show a little better. And I don't think the moon is up yet. I think the moon is probably just going to be coming up. When it does, we're going to see a kind of a glow that's going to permeate, a little bit of a glow. But our filters take away most of it. But look at this. It's gorgeous.
That's excellent.
That's really pretty.
I hope that makes a good processed image.
It will. It certainly will.
Very pretty. Folks, can you hear me okay now? Doo-dah.
You're going out as loud as I am. And Michael Hendrick has a question. Okay, I'll wait for it. All right. Now you got to keep in mind the perspective here. That's another thing, that's really tough. Okay, is you have to understand the perspective. You're seeing the dust tail, but it's kind of into the page and behind us, or behind the comet coma. And this tail here, this one here, is kind of also into the page a little bit and on an angle toward us. So this part here is much closer than that part there. And so taking into account the whole perspective, that will tell you, how the geometry works, and it's easier to see it that way and understand.
Yeah, I said the other night, if you look at the shape of that, if you imagine you're holding an old-fashioned folding fan in your hand, well, the base of the fan laying in your palm.
Oh yeah.
That's the head of the comet, kind of pointing toward us, and then the fan is extending away from us.
Yeah, that's a good point. That's a good point. And so I think that's pretty interesting. And again, this color and the way this looks is really, really stand out. It stands out tonight quite well. Yeah, nice.
That's great.
All right. Well, I'm going to do something even crazier here now. I'm going to set us to a 90-second shot just to pull in even more. And then I'm going to increase us to 350 gain, which I won't mind telling you is noisy, but let's do it. So here we go. So this is a minute and a half, and the telescope is guiding well, so we should be okay. Hello, Mazif. How are you? DD, what's happening? Nice to see you here.
Tara and Marianne say I'm still soft.
Well,
other people say I'm fine. I don't know what to tell you.
Right, well, we are matched right now, so...
Okay.
I'm looking at the levels.
Well, while we're waiting.
Well, you could talk louder too. I mean, that's also a possibility. Or
Okay, I'll try talking louder. Plus, I'm almost chewing on the microphone. Hello, DD. Carry on.
All right, no problem.
Yeah, one thing you should note too tonight, folks, when you look at that image, and like you sort of visualize that fan shape fanning away from you, the comet has moved away from us quite a bit since it was at its closest, and as it gets farther away, it's like watching a car or a train go down the railroad or the highway. It's apparently slowing down, and I suppose it is actually slowing down too as it moves away from the sun, but just as we see it in the sky, its rate of motion is decreasing now. Ultimately, this may make an effect on how long an exposure mark runs without it blurring.
Look at that.
That's great. Yeah,
that's
catching the blue now too.
Yeah. Okay, so this is good. So we'll color correct, and now that blue is standout. This is a minute and a half. Now this nucleus is going to be just a little bit blurred, but that's okay because we're going to try and capture this to see most what we're trying to find, and that's actually the blue of this object here. The blue is going to be beautiful.
It is.
All right, let's do this.
And then you can still see the dust tail, the wide part of the fan up to the upper left of the comet's head.
Yeah.
And that's basically the color of sunlight.
Yep. You're absolutely right. Okay, so so the comet right now is basically just over a third of an astronomical unit away from us. Okay, so that's basically 0.35 astronomical units, or 53 million kilometers. Okay, and that's how far away it is. That's a lot farther than it was before.
Yeah, when it was closest, it was 26 million miles, and now it's 31 or 32. Buzzer, I'll be right back.
We'll be right here. Okay, so look at that. Now we have this beautiful image here. This is stunning. Wow. And in case there's any doubt about what we're looking at, let me just throw that right out there. There you go. That's our label. All right, so now, so as we go through that, we're not going to only exclusively look at the comet tonight. We're going to look at other things as well. But it's just cool. Oh, HR 8799. I know all about that. I talked to the scientist that took that image, the astronomer that took that image of that planetary system. It was one of the first images ever taken in direct light. And it shows a whole solar system. Let me just explain. Michael Hedrick is saying that the Gemini Observatory did a view of HR 8799. It's a planetary system. And it was made using the Gemini Altair Neri and acquired on September 5th, 2008. Okay, that image, again, was the first one ever taken of an entire star system, planets and all, but they blocked out the star in the middle with an occulting disk, so that was pretty cool. And that way, I did a talk on HR 8799, as a matter of fact, so that's how much that's why I know about it. Hello, David. I didn't say hi to you. I apologize. And right now, as Daryl told you, David asked how many years for this to orbit the solar system, come back in. If it comes back in, it's called a periodic comet, meaning it'll come back again. And right now, it looks like that might be about 50,000 years. Kind of hard to figure it out. But still, that's the beginning of our estimate. We'll probably be able to refine this as we get better orbital elements for this. In any case, Hi Alpaca said this is really awesome to see. From what I read, it's correct. The last time this came to Earth was in the Stone Age. I wonder since then if it has gotten closer to Earth. I'm not sure that it's actually been disturbed in its orbit to come closer. I'm not sure about that at all. Sometimes that can happen. Jupiter has a massive effect on these, and so of course so does the Sun. The rest of the planets to a lesser extent, but still noticeable. All right, so that is a possibility, without doubt. So I don't know the answer to that question. I'd have to look that up. I don't know everything. I do know some things, but not a lot. When it comes to certain things. And we have a tumbling satellite right here.
Yeah, I was going to say, tumbling rocket body or something.
Yeah, because you can see how you have a dash, and it gets dim for a while, then it lights up again, gets dim for a while, lights up, gets dim. That's what happens when something's doing this in the sky. It's going through very bright, and it gets very dim, very bright, and then very dim as it's rolling or spinning end over end. So it's kind of doing this kind of thing, right? Where it's coming toward us. Now it's very dim, okay? Then it's going to be very bright, and then very dim, and so that's how we call those. I call those. I don't know if anybody else does, but I call them tumblers.
It looks like a TIE fighter or something is shooting at the comet.
That's right.
Pew, pew, pew. Yeah. Pew, pew, pew.
Speaking of tumblers, I just want to show you. This is a SkyTour live stream tumbler that I got. It's really pretty. It's really cool. And it's actually kind of hard to see. Let me see if I can show you. This is the the Seagull Nebula, and it says Seagull Nebula on it, and it's actually has our logo and stuff on it. It's pretty cool. And eventually we'll be offering things like this, once we approve designs and get them out and start to get a store up. But once we do, they'll probably be available at some point. Now is not that time, but it's going to be soon. I would think soon. And what soon mean? I don't know. But hopefully in the next few months.
Pew, pew, pew.
Daryl's in rare form tonight, folks.
Yeah.
This looks great.
My chicken and noodles were excellent. I'm in a really good mood.
Excellent. All right, so here's what we're gonna do. We're gonna do our best to kind of migrate this a little bit over here. See if we can get some more detail out of this. Little color correction shows that tail very brightly. All right. And again, this is a minute and a half at 350. And let's increase it. Crazy bright, way brighter than we want to, but it'll help us when we try to bring out that tail. So this is what we're doing now, is bringing out the tail. Look at that. Now that tail is really bright. And let's actually add another adjustment to see what's really there. Okay.
Jeremy, this is a good comet. It's not a great comet. Hale Bopp was a great comet. They don't come around that often.
Yeah. I want to say hello to our Asian friend. I can't read your name, unfortunately. I wish I could. But hello there. And hello, Jeremy. How you doing? Jeremy B is with us. I don't know. This kind of looks like a cool comet. We're making it cool anyway, aren't we? Hey there, big fire bear. What's going on?
It's pulsing at me.
Yeah, the comet is actually in the constellation Auriga. So it's kind of almost straight up, in the sky right now. And it's going to kind of stick around there. And around February 10th, it's going to be in the same field as Mars. And we'll be able to see Mars in the same view. It'll kind of look like, well, this isn't Mars, but it's a red star. And we'll kind of see it in the same view. So that'd be kind of cool. Kathy Pernisek, it's nice to see you. How are you? All right, so let's take this brightness down a bit and get us back to our earlier brightness. And let's let it tell me what it wants to do. What would it like to do? Okay, so that's what it wants to do. Nice, beautiful green color there. Beautiful blue-green color in the tail. That ion tail, distinctly different color than up here. Those ions, again, at a slightly different frequency. Yep, very nice.
It's blinking at me.
What's blinking at you?
The comet is.
It is?
It was. It looked like it has something to do with your mouse. Your pointer.
Oh. Oh, I didn't see that.
Not doing it now. It's done it several times.
Okay. So if I drop this down, we can start to see a little more, but you can see now this line. Okay, that's the fact that it's moved. All right. And just to show you, okay, we'll clear this now. Actually, let me do one more image because I want to show the ion tail one more time here. Okay, and we'll just save it now. Again. And then save it exactly as seen.
Pew, pew, pew.
And you can get all these by going to SkyTourLive.org and scrolling down, and it'll take you to the live server that is available to all of you. Now, if you go there also, on the upper left, it'll take you to this stream, SkyTour live stream, but on the upper right, it takes you to the Patreon. If you want to subscribe to us and get these images in ultra big resolution and fully processed, well, you know, we have tiers for that up there that you can do if you want to. You know, we have a $5 tier, which is a shout out. $10 tier gets you 4 of our best images each month, and I could include one of these, the comets, in there. And then we have a $100 tier and a $200 tier. We might put in some more, but the $100 tier gets you our entire paywall of all the best images we've taken. Really huge, very, very high resolution, and just stunning, gorgeous imagery. So that's another thing, and we'll be happy to preview that with you if you want to see it. All right, and at the $200 level a month, you actually, and who can afford that, right? You actually get a guided tour with us. You come out with us and you say, I want to see galaxies, I want to see this, I want to see that. And we'll take you there, and then we'll process your images specifically for you. All right, so you can get those. So that's pretty cool. It's a little benefit. And, of course, you get everything else that goes with that as well. And we're going to manage some other intermediate tiers at some point, you know. So that's pretty cool. All right.
The pew-pews are going away.
Oh, okay. Hey, Dragonfly 2, how you doing? All right. Izabela, thank you for putting out the Patreon for us. Thank you very much. Okay, so now that we did this, let's clear this and get out of the stack for now. I'm going to do one other thing now. We're going to go here and go into our night vision mode. All right, and that's this mode right here. Okay, so this is live. And you're seeing this as 1 second image, 1 second images. 1 second exposures, I should say. And since we know it's the comet, I'll take that out for now. All right. Hello, PG. Nice to see you. Now, I want to show you something. All right, we talked about the comet moving. All right. So we're going to zoom in here.
Oh, nice.
First,
it's almost like it's going through a field goal, those two stars.
I know, and so what I'm going to do is I'm going to move this over a little bit and get us a little more centered up here. It won't be dead center, but it'll be close enough. This will be good. All right. Then we'll zoom in again. All right. All right. Now what we'll do, just so you can see it really is moving, I'm going to draw a line. And that line is going to be maybe right here. All right. And now you'll watch, you'll see the line doesn't move against the stars. Okay. And you'll see this comet is going to move against there. In fact, it's already moving. You'll see the comet is going to move a little bit to the right in this image. And it won't take long before it's on the other side of that line.
But maybe we'll see it move slower than it had been.
Yeah. I want to say hello to Marc Nelson. This is someone I know. Hiya, Marc. Thank you for coming on board and checking us out. Good to see you. This is a comet we're looking at right here, Marc. It's, oh gosh, it's 50 million kilometers away. It's speeding away from us at pretty high speed. In fact, it's moving so fast that this line I drew in here will allow us to see it cross the line here in just a few minutes. That's pretty fast. And Cyclone has a question.
He did.
Okay. All right, Marc Nelson, thank you for the compliment. That's great. Thank you for coming in.
I guess we could say already that the comet is moving left to right.
It looks it, yeah.
And Mars is out of field to the right.
Yep. And it's heading for that.
Roughly south.
Yeah. And to understand the way we're facing here, south is not down in this image. Let's go to Stellarium for a second. All right, and I'll show you what I mean. But you watch it moving here.
Uh-huh. And I think it is markedly slower moving than it was
oh yeah,
the other night when we did this.
It's moving slower, apparently slower, right?
Yeah, and it's actually moving away from us, folks.
Mm-hmm. Oh. Here, let me get rid of my line for a second here.
Marc, it's a third of an astronomical unit, maybe 31 million miles.
Okay, so I'm going to center us up on the comet here. Okay, this is where we're looking right now, and we're gonna center up on it in the same orientation that the telescope is looking at it. All right. So if we zoom in now, you'll see that when you start to be able to read this, you'll see it's upside down. So the comet is actually heading to the south, which is this way. Let's zoom out a little bit so you can see which direction that means. It's not directly in that direction, okay? Let's go back here. Okay. So there's Mars. There's Capella. All right. So it's literally heading in this direction. So when I come back here, I can put the line in a way that makes it more obvious. All right, I'll put the line in right here. All right. We'll do it right there.
Those two stars, that's the two called the goal posts.
Yeah.
Earlier, right? So
yeah.
It's moving down and to the right.
Yep. Just to the south. Yeah, this way. All right. So if we put that line in. All right. Oh, want to do it in a way that's pretty obvious. All right, let's see here. Okay, now if you watch it, see, we have a tiny bit of wind out there. You see the stars get elongated for a moment, then they go back. So you'll see that the comet's going to go completely below this here in just a short order. In fact, it just did. So what's happening is you're actually watching this. You're watching the universe change before you live. That's exactly what's happening here. James Dugan, hey there. Very nice. So it's certain that the comet is moving, and it's really, it's obviously moving. As far as the direction it's going, it's heading this way. So that's the direction that the comet's actually going right now. I'm not sure if we'll see it with the all-sky cam. It might be a little small, but we could try it. Because that's the other aspect of what we have here. I can actually bring up the all-sky cam as well. And so let's get rid of this stuff here. That stuff. And let's do that. See if the all-sky cam will show us what we want. Alright. Alright, and I changed the settings here because we want a slightly longer exposure on this. Alright. Okay, and right now it's 10 seconds. We're going to make it 15,000 milliseconds, which is 15 seconds. Okay. And we'll save changes. And preview.
Cyclone has a question.
Alrighty. Alright, let's go back to the comet while we're waiting for that to come in. Cyclone says, I had watched something earlier and it was talking about black holes. My question is, would our atoms get shredded infinitely as those atoms as thousands? I don't know what you're saying there.
I think he's saying once the black hole spaghettified us and tore us atom from atom, would those atoms in turn get torn particle to particle? Like subatomic particles, you know, the constituent particles of atoms?
We'd probably get, when you get spaghettified, you get torn apart. And with the energies and so forth, you can be sure that your atoms would all end up being probably plasma. You know, that is to say, ripped into protons, separate electrons. So that constitutes being torn apart, yes.
About as torn apart as you could be.
I would say so.
Yeah.
All right, this is cool. Now let's see here. Let's go back to our all sky and let's go and do our full screen shot. And look at the full screen preview here. All right, where we're looking now is up in Auriga, which is here. And the comet.
It's the bright star just above center.
Yeah, this is that's Gemini. What am I talking about?
Yes, there's Capella there above center.
Right there, and there's the kids. So right now we're on our way to Mars, which is right here. So we're somewhere in here, and so as you can see, there's not enough pixels to really tell what we're looking at. The comet is a small fuzz in there, and the stars are the brightest dots. So the comet's in there somewhere, right around there. Interesting. This
is a problem Bill had a problem with on his meteor streams when he was trying to get a little more wider field of view, you know, with a different lens, camera lens, that the image scale shrank and the meteors didn't look as impressive because they were shorter.
Yeah. A faster lens is better, but you know, isn't always the best. All right, we'll come back to the comet. Let's go check out something else while we're here.
Cyclone, I'll give you something to chew on. Depending on the black hole, well, how big the black hole is or how relatively small as black holes go, the smaller black hole is more likely to tear you piece from piece than the bigger black hole is, because it has a sharper gravitational gradient, or a tidal gradient, I guess you could say. The smaller black hole is worse for spaghettifying you than the bigger black hole is. That is, you can get a lot. Some say you can enter the event horizon of a black hole and not necessarily get spaghettified.
That's all conjecture, though, and
well, it's all conjecture.
The idea is, if you're going to make use of an Einstein-Rosen bridge, a wormhole, one of the ways to do it is to cross into the event horizon and utilize it from there. The trouble is, wormholes, if there even exist, we haven't ever seen one, would be notoriously unstable, and you wouldn't know where they're going to necessarily, if they're going anywhere.
Right.
So, but that is an issue. I'm going to take us now to an object that I think is really pretty, and it's literally right nearby. It's called the Flaming Star Nebula. Just to show you what we can do. All right, so there it is, and we're going to go now, and the telescope won't move that much, but the object will be in the middle of the view here just in a moment. Okay, there we go. There it is. It's a nebula, that is to say, a hydrogen emission region, but it's also a region where there is a gorgeous reflection nebula. Now, we have nebulae of several kinds. We have dark nebulae, we have reflection nebulae, and we have emission nebulae. H alpha regions are called. Usually the H alphas are the reddish ones, and they will be the ones that people will look at and say, oh, this is where stars are formed, and they'll be right. Okay, but the blue ones are areas where there's dust. There's a lot of dust in the universe, and this, when I show you this image, when we actually make this image, you'll see what I mean by that. And before we do that, I'm going to actually set up our focus here, because I'm going to do a focus run, which I like to do. If you notice, when we go out of focus, the star colors show up much better. That's what's kind of cool about doing this, right? And so we're going to do a focusing run to get the telescope critically focused. All right, and that's what we'll do right now. And we're going to have the focus scan inward. All those stars are stars that it's picking to use in its analysis. And we want to try and get the best size image, the tiniest image that you can get amongst all these stars. Right now, there's 81 stars that have been used in this right there. And you can see now it's 124 right there. And what we want to do is make a curve. I want to make a parabola, like a curve. And that parabola curve, at the bottom of that parabola curve will be the best focusing position. And so that's going to be kind of like, it'll look like this, right? It's going to be like a line like this. And at the bottom right here, this is going to be the main, this will be the best point where it focuses. And that's kind of what we're after. So you can see the curve is going down, and then it's going to start coming up. And it's going to come up to a certain point and say, okay, I've got enough. And it's going to put a line in here just about now, probably in the next patch. All right, so we'll see, there it is. And that's our best focus for now. Now that'll adjust. You can see it's adjusting even now. You can see that changing. And then once we get the best focus, we can tell it to go there. I'm focusing right now, Mark. I haven't looked at the Rosette Nebula yet. Okay, now we're going to go to best focus. So now the telescope is going to go all the way back through and all the way back to get to the best focus. All right?
Think you will look at the Rosette tonight?
Sure, we might be able to do that.
Okay, I mean, we're in a really rich part of the sky right now. We're not too far from the Crab Nebula.
No, we're not, yeah.
The flaming stars you noted earlier, and
yeah,
there's all sorts of cool stuff up in this part of the sky this time of year.
There are.
Comet star of the show, so to speak.
That's right. Okay, this
Thank you, Kathy.
Oh, thank you, Kathy. All right, this is well, we're there, but something it's oh, duh. Okay, never mind. All right, here we go. All right, so now we'll go slide back into the best focus. Goes all the way across, all the way back. Okay, and the stars are going to now be pinpoints. And now we can get out of the best, out of this focusing thing. Turn on temperature compensation. And now as the temperature changes out there, right now the temperature is 10.69 Celsius at the focuser. And as it changes, the telescope we will actually be able to see that focus change a little bit, and it's because it can be compensated by the temperature compensation. Okay, let's do a 35-second photo of the flaming star. We're going to go down to 300 in the sensitivity here, because we won't need that much for this. All right, and this is pretty. So here we go. Now we'll go into our stack, and right now the progress is over there. If you're looking for the progress, very simple. It's right here. That's our progress right there. Okay, right there. There it is. And that yellow bar gets all the way across. It means we'll be ready, to see the image. Okay, so that's what we do. So we are 6 seconds, 5, 4, 3, 2, and now we'll see the flaming star. So be ready for a pretty image. Ready? Here it comes. Okay, and we're gonna look at that. Wham! That's pretty. There's the flaming star nebula. All right, this is the star that's the culprit, if you will, and it's really a very gorgeous star, and it's causing all of this gas in here to be glowing like this because it's the hydrogen's being ionized. So the one electron on the hydrogen atom is going flying off the atom by absorbing energy from the ultraviolet light coming from this star. And then it's going to fumble around outside for a little bit, colliding with other particles, and then it's going to drop down. And when it drops down into the atom again, it gives off light. And that giving off of light is in mostly the red realm. So it gives off other light, but it's mostly the red. So that's why we see red nebulae, and they're called H-alpha or hydrogen alpha emission. All right. But if you notice, if we zoom in, you'll see something else. It's not just red light we see. We also see some weird blue light. All right. Look at that. That's crazy. What is that? Okay. That is actually what we call the reflection nebula. Because mixed in with this hydrogen gas, as Daryl and I have talked about before, is dust. And these are little tiny, tiny particles of dust. All right. And these tiny particles of dust are really interesting because it's those tiny particles that are very, very efficient in scattering the blue light from stars, which is the highest energy light, the shortest wavelength. And that blue light gets scattered very easily by these dust particles in all directions. So that's why you see that this light is blue. That's also why our sky is blue, because the molecules in our atmosphere are also very efficient at scattering the high frequency light from our sun, the blue end of the spectrum. So we see that blue end of the spectrum everywhere we look, because the molecules are scattering the blue light and letting the rest go through. Okay. That said, it explains why sunsets are red. You're looking through more air over the curve of the Earth, and so more air means more blue light is getting scattered. So the sun, what's left is less and less blue light, and since it's red, orange, yellow, green, blue, indigo, and violet, it means that we're getting mostly red, orange, and yellow coming at us. So the sunset looks red, and that's why.
I once saw a sunset rainbow.
Wow.
And it was with the very last rays of the setting sun. The rainbow was red.
Wow.
The only color that showed up was red, a red bow across the sky.
That's really cool.
Then the sun went below the horizon and it vanished.
Wow.
That was up at 11 Mile State Park up in the mountains west here.
That's cool.
West of here in South Park, where the TV show is.
Hey, I'm that fat and big boned. Cartman. All right.
Of course.
So I'm giving a little contrast here so you can see these beautiful colors. Let me see if I can do a color correction. There we go. All right, so now you actually see that better. And I'll zoom out so you can see the entire nebula now that we've got more data. We've stacked 7 images. Look at this.
Izabela has a follow-up question for you.
Okay, Izabela. Izabela says, why does the sun look yellow when it's almost white? Actually, Izabela, for precisely the same reason I just talked about. The blue light from the sun, all right, is coming to us. The spectrum of the sun is effectively white, okay? It's got that red, orange, yellow, green, blue, indigo, and violet color in it. However, the molecules are scattering that blue light, making the blue sky, right? So that light isn't made up for anywhere. It's taken out of the spectrum from what reaches your eyes. So the sun looks yellow to you, okay? But up in space, the sun doesn't look yellow. It looks a little more white, all right? So that's kind of interesting that, you asked that question at a perfect time, Hope that makes sense. Now, this is the Flaming Star Nebula. Down here is, right there, is another nebula. It's right here. It's down kind of where my head is, okay? And that's actually called the Tadpoles, all right? It's another region, and it's actually a little bit closer to the Comet, actually, if I recall. Let me go back and see. I think it is. Okay, so, all right, the Tadpoles are over here. Where we are. Yeah, because they got the... we're upside down, so it's to the lower. Yeah, so it's here. Here's where it is. So that might be...
It's the letter Y cluster, isn't it?
Yes, that's the Tadpoles. Okay. Yep. So again, we have a bunch of stuff in this region that are just fun to look at. So we're going to spend a lot of time poking around in this tonight. Why not? And even with the moon coming up, it's just past full, but no problem. We have filters to prevent the moonlight from ruining our photos for the most part. So I think that'll be kind of cool. All right, so we have 11 of these. These are this is the beautiful Flaming Star Nebula. It's just beautiful. And let me just kind of make that look a little bit brighter. Look at that. Now here's the thing, okay? You're seeing this live. This is live, right? This isn't a photo. This isn't a picture in a book. This is live. You're seeing it as it's happening. And I think that's the coolest thing about what we're doing, Let me pull that out. We've seen it. All right. All right. Hi, Alpaca says, can you imagine doing your entire show in that voice as Cartman? No, as I ski, you guys. I'm going home. Yeah. All right. Okay, so we got 13 of these. So I'm going to pause this here, change the name up here to Flaming Star. And the name might change up there, right there, up at the top there. This is the name that's going to appear in the directory. So when you go looking for it, you look for that directory name, right? So we'll save it, and we save our astronomical file format, which is a raw file format that we can process as astronomers and as people that want to do it for fun. And then we save it exactly as seen, so you get just this picture. And what that means is you get this image that you see right here, and that's beautiful. So now we'll clear this, get rid of our stack for the moment, go back to our night vision mode, okay, and with the night vision mode now, we're going to move to another object right nearby. Okay, and it's this thing called the letter Y cluster. It's at the lower left corner. Remember, what you might forget here, which is easy to lose your orientation, is if you look at the telescope, it's leaning back. It's upside down, so you'll notice that the letters are upside down here. Okay, so we're going to go here, and that means it's at the lower left, which is right down here. So when I tell it to go there, you're going to watch the telescope head down in that direction right now. So there we go. There it goes to the lower left. And we end up coming to this new nebula here in the view. You can see it right there. All right. And it will center up. And then we're going to go a little to the west, center it up a little bit. And if you're thinking about this, any of you, then the answer is yes. We can take these and make mosaics where we actually make gigantic panels. I did one of the Orion Nebula all the way to the Horsehead, which is beautiful. Lots and lots of photos. Okay, so this is now, we have our guide star. You can see the guiding is right here. That's the guider, and it's stable. So we're going to go from 1 second, which is 1,000 milliseconds, and we'll take it up to 45 seconds. All right. And we're underway. You can see by our yellow progress bar down here. When that fills up, and if you can read those numbers, it's counting down. Make sure you're in 1080, by the way, 1080p on the stream so that you can actually see all this. Let's get out of that here.
Izabela and I were talking about a mosaic, Mark.
Oh, you were?
She wanted to see what was off screen below the flaming star. And I said, I've always wanted that too. And
you mean the arc?
I don't know. When we did the mosaic before the area here with the tadpole and the flaming star,
that wasn't covered.
That part wasn't covered. Yeah. Maybe that's why she's asking.
Yeah, I'm sure. Yeah, you can see it. Okay, here is. Okay, it looks like the moon is up. I can tell by this bluish cast. So let's color correct and get rid of the moon glow here. There we go. All right, so now we're seeing another amazing location, and the flaming star. You can see just the edge of the flaming star right up there in the corner that you see. That's the part of the flaming star up there. And then this guy here, this is what's called the letter Y cluster. That's those stars. But then there's something in this, which is really cool. And we are going to now have our second frame here that we're stacking in just 1 second. And then 2, we got them. So now I can zoom in. And you can see we have these things right here. These are called the tadpoles. Okay. And the tadpoles are a very interesting location. If I just pull this back a bit to kind of soften things up a little bit, you can see what we're looking at. And pull this in. I'm pulling in the levels. See, this is our data right here. See these curves. These are our data, red, green, and blue data curves. And these curves are the intersections on the curve. So if we ride up that curve, space is here. Space gets blackened out more. Okay, but noise is increased if we go too far. All right, so we come to about here, and we can actually soften things up here. So if I grab this right here and pull this way down, you'll see that we go right down to having no nebula, and then bring it back up slowly and pull it in. We have what's called a very high dynamic range on our processor and our sensor here. And depending on where we put this, we can get rid of all the noise and see just the objects we want to see, and do all kinds of interesting manipulations on the data. Okay. None of this is permanent. The FITS file that we make is an astronomical file format that's raw, and you can make this happen like in a Photoshop application. But if you don't want to do that, all you have to do is go to SkyTourLive.org, go down, head into our directories, follow the instructions on SkyTourLive.org for getting into the directories, and go and find the images you want. Hey, sloppy scientist, how are you? We were looking at the Comet earlier. We're going to go back to the Comet in just a few minutes. All right. Waiting for some more. We got 5 stacked here.
Cyclone wants you to do your Vader voice.
My Darth Vader voice. Well, the Vader bottle is not nearby, but I can get it in a bit. Yes. By the way, just if anyone wants to know, I'm not sure if anyone wants to know, but March 2 through 4, I'll be in Pasadena. I'm in Connecticut now, but I'll be in Pasadena at the Alien Con conference. I don't know if any of you are going to be there, but you'll get a chance to meet each other and say hi. And I'll be there on behalf of A&E, who is a partner in that conference, because I do the show The Proof Is Out There, and this upcoming season, I think I'm in 40 episodes, I think. So they want me out on a panel. I'm also going to do a talk, a really cool talk. It's called The Unorthodox History of Earth. There's going to be like 1,000 people, I think. There's several thousand, but at any one time, there's 1,000 at the talks. And what I'm going to do is I'm going to do the history of the Earth. It's very unique. I actually put the entire history of the Earth on a roll of toilet paper.
I knew it.
And I go out into the audience, and I unroll it we reach all these different milestones in the Earth history. And I toilet paper my audience. Yeah, I get to do that, and they love it. So it's actually kind of cool. And I gave them a choice of what they wanted, and they unanimously said, toilet paper history of the Earth, man. Okay. And along the way, you'll find, it's 120 feet long, and only the last thing, the width of a human hair, is everything we've ever known as a human species, in terms of our modern history. It takes us from a time where history was first recorded in ancient Sumeria on the cuneiform tablets to the present day is on the width of a human hair on a length of 120 feet. There you go. And to see it is remarkable. You see that dinosaurs are recent history, not ancient history. They happened less than 12 inches ago at this scale.
Is it still the same roll of toilet paper?
Yes, I've used this toilet paper over and over and over. Well, wait a minute, not that way. Yeah, actually, I've modified it heavily over time, and now I've made it much more resilient. It's not really toilet paper anymore. The first one was, but it looked kind of ratty after one use, so I opted for a different material.
Cheap toilet paper would probably work better.
It was actually I used this wallpaper stuff that crepe material, but I spent 5 or 6 hours putting all of it together. I actually drew the lines for each 4-inch sheet, all the way down the whole thing, and then they ended up a long time.
That's dedication.
Yeah.
Never think if you went and bought one of those rolls of institutional toilet paper, it's neither soft nor gentle.
And it was like a foot in diameter.
Yeah.
See, I could get one of those and do the history of the universe. Hang on, I'll show it to you. Okay. While we're stacking here. Okay. So let me bring back my background here a little bit. Give you a little preview. Okay. All right. So here's the roll of toilet paper, and really, I actually kind of got it down to a little bit of a science. So, this is actually the end. See, Earth forms, and that's it. Sheet 298. Earth forms, and then you unroll the different sheets, and then finally you get to things like the moon forms, and it goes on and on until we get to the present day. And each sheet is 34 million years.
Has the TSA ever asked you what the heck you're doing with that when you go through luggage inspection?
I did have a few incidents with it, and it always ends in a comical way. It did.
I would hope so.
It always ends comically. Yes. No. They're like, because I don't put it in my luggage. I put it in my backpack. And like one agent said, we have toilet paper on the plane, right? And I said, yeah. I noticed my toilet paper has words on it. And he goes, just go through. I didn't explain to him what it was, right? So that's crazy. But that's the whole point of this, though. The whole point of this is to show history, show astronomy in ways that are unique and different, right? I mean, and memorable. I hear people tell me years later, I remember your toilet paper history of the Earth that you did, and how it came across so well to everybody. I remember everything you said. It's like that means it was a success, right? So that's all good. I remember I did this with Bill New York Skywatcher at Pine Bush one time, and I was actually having him hold the other end to do it outside. We were doing it outside at one point. I did it as a special presentation for his at his house with everybody, and so I ended up doing my thing, unrolling it. And he was on the other end rolling it up. Well, he dropped 1 billion years on the ground, and 1 billion years went rolling on down the hill. It was actually pretty unnerving to watch 1 billion years roll away. But we got it back. So here we are. We've got 14 stacked. We'll do this last one. Look at the tadpoles. That really looks pretty, doesn't it? I'm going to add an enhancement here. Okay, watch how much clearer it gets. Look at that. Now you can actually see, I added an enhancement here called an unsharp mask, a dynamic unsharp mask. And you can see how the tadpoles now have a lot more definition in them. Look at that. Isn't that beautiful?
That's very nice.
It's really pretty. So what I'll do now is go back.
And there's always, look at all those curved lines of stars inside that.
Yeah, like right there.
They look like they're associated, you know?
Yeah, like that. Yeah. Okay, let's, again, just because this goes away doesn't mean it's the last time you're going to see it. Again, it's all available right here at SkyTourLive.org. That's our portal. We are a startup nonprofit, so, you know, and anything you can do to help us out would be fantastic. You know, and again, I'm not NPR. I don't beg for money, but we do run on donations. So look at that. I just color correct and make it look even better. Look at that. Wow.
Can you zoom back in on that some?
Yeah, we can do that.
Please. No, there to the lower right of the tadpoles in particular, those curved lines of stars. I mean, they're so evocative of, like, you know, currents or flow or, you know, the cloud banks and stuff.
Yeah.
So we talk about this, folks. You know, sometimes you'll see random, looks like lines of stars in the sky, and sometimes it looks like they're almost there for a reason. This is one of those cases, you know. It's like like what was happening inside that star cloud and star cluster, that those stars formed along those lines, like the currents flowing in the cloud.
Yep.
Always how it seemed to me.
Yeah.
That's really something.
I'd like to answer Maya Leon's question. By the way, hi Maya, good to see you. They're called the tadpoles because they kind of look like tadpoles. See, these have this look of like the head of the tadpole and the tail, right? The head of the tadpole and the tail. So that's why they're called the tadpoles. Very, very cool. But thank you for that question, as always. You're on top of things. Okay, so zooming out now. Okay, this takes us out pretty far. And there you see the whole thing, and that's really pretty. And what we can do is we can, you know, really blacken up space and give us a little bit more contrast. And what I'll do now is we have 18 stacked now, and I will actually pause it here and save this. And then save it exactly as seen. So you can get this exact image up at SkyTourLive.org if you want to. Just scroll down and look for the Take Me to Cool Images section. And read the instructions for how to get to it. Ronald is here, ERRT Radio on Mixlr. Good to see you, Ronald. Thank you for coming out and checking us out. Ronald is a friend of SkyTour Livestream, a very good friend, so he's well known to SkyTour live streamers. All right, so we're going to clear it now, get rid of it. And let's go back to our night vision mode. Okay, here we go. Here's our night vision mode. All right.
Ronald asked if this is the new camera. I told him it's the old improved camera.
It's the old camera that has had servicing done. Tara and Marianne actually went out and serviced the camera. And as you can see, the images are spectacular.
Yay, Tara and Marianne.
Yeah, they're just astonishing ladies, let me tell you. All right. Now, let's, okay, now, just for the record, okay, there's Capella. Right, excuse me. There's Mars. All right, there's Capella. The Comet is just around here, so we'll come back to that in just a minute.
No worries.
Okay. while we're up in this region, there's no reason not to check out another object that I like out here. In fact, we'll do it this way. We'll just we're gonna go to the Crab Nebula.
Cool.
Yeah, the Crab Nebula is beautiful. It's a structure that is left over from the explosion of a star. All right, it's actually a stellar remnant from a supernova.
That star just to the lower left. I can't read it.
Tianguan.
Say again?
Tianguan.
Okay. The
Or
Zeta
Tangu.
Tauri, if I remember correctly.
Yeah, we'll just
That's
click on
the
it.
tips of one of the horns in the bull.
Yeah,
Taurus.
right there is Zeta Tauri. You can see that. That's the Greek alphabet letter Zeta. As astronomers, we learn the Greek alphabet early on because that's how we designate stars in some ways. We also have, the Henry Draper catalog, Leonard Dr. Strung. We have the Smithsonian Astrophysical Observatory Atlas. We have the Tycho star catalog. It just goes on and on and on. There's so many star catalogs. But we're going to go to the Crab Nebula now. And you'll notice the writing is up right now because the telescope has come back from looking back over its head to now looking just about straight up. And so this is going to be a most beautiful view. And you'll see it. So we're going to zip over to it now.
Ronald wants to know what type of star caused the Crab Nebula. Would it be safe to posit that it was something like Betelgeuse, perhaps?
Well, in its original form, the star was probably an O-type star.
Yes.
So that's the hottest and bluest. And the O-type stars, they end their lives in explosive glory, And they only live about 10, 15 million years. That's as long as they actually get to exist. All right, let's...
Would the blue supergiant star necessarily have turned to a red supergiant star before it exploded?
Yes. It
Okay.
would. It would go to a supergiant stage prior to the explosion. Because that's the evolution of stars. Even the old supergiants, when they leave the old giants, when they leave the main sequence, they traverse up to a red giant phase, right? And the evolution varies depending on the stellar type, but they end up going up another state called the asymptotic giant branch, okay, eventually, and that's where they end up going all the way up into a massive red supergiant, and it's from there where things become rather they go downhill rather fast, and so within a few 100,000 years, at that state, they will end up. In fact, even less, they'll actually finally exhaust all of their nuclear fuels and explode in a cataclysmic eruption like this, where they totally rip themselves to pieces.
So it went from an O blue star to an M red star, but a great big one.
That's right, like Antares, like Betelgeuse.
Yeah.
Okay, we'll do 20 seconds here, because that's really all we're going to need to show some of the cool detail here. All right. So we'll go into the stack and clear the last stack if we have to.
Ronald, this is the star that exploded, and we saw it explode in 1054 AD. It was so bright they could see it in broad daylight. It was super bright at night.
Mm-hmm.
It was up there for a long time. The Chinese took note of it and wrote about it. And,
Yes, they did.
And this is what we see 1,000 years later.
Yep, this is it. And this is only one stacked image right now, and we see two. It gets instantly better, as you can see. All right, color correct it. There you go. Look at that. All those filaments are interesting if you look, and we can't we can get in closer, but we need to wait for the stacking to remove a lot of the noise. But you can see these red filaments, you can see green filaments. The red filaments are hydrogen filaments and other elements, and the green filaments are predominantly oxygen filaments. Now, whenever we talk about this, I'm always talking about it being hydrogen or oxygen. Well, why not other things? Well, there are other things, but hydrogen is the most prevalent and abundant element in the entire universe. So hydrogen is going to play a major role in what we see in any nebula. Okay, second most abundant is helium in the universe. Okay, because hydrogen in a regular star is by fusion made into helium. Okay, an isotope of helium. And then next after that, believe it or not, is carbon. Okay, I'm sorry, oxygen. Right, oxygen is the next most abundant. And then comes carbon. Carbon's the fourth most abundant element in the entire universe. So it stands to reason that life is going to be based on carbon, because carbon is a very, very flexible element. It can bond with more things than any other element in the entire periodic table. And the nice thing is, the thing that makes carbon so unique is that when it bonds with things, it can also break bonds with things in a fairly unique and easy way. And it all comes down to the energies that are required in the atom and in the universe for combining and disassembling certain molecules. And carbon is, well, carbon's at that magic point where it can bond with more things than anything else. Hundreds of thousands of bonds it can make with other elements, unlike silicon, which is the next most likely one. In that row, that vertical row, you have carbon. Then right below, you have silicon, right? Yeah. Well, silicon, people say, what about silicon-based life? I'm not holding my breath on it. I tend to be a carbon bigot. Okay, so I am kind of prejudiced toward carbon. But
Did you watch that video I sent you?
I have. Okay. And the reason, though, that I say I'm a carbon bigot is because silicon tends to make crystal structures which are tenaciously bonded. So it's kind of hard to, for me, to imagine that there would be silicon-based life. It doesn't have the robustness, it doesn't have the flexibility, and it doesn't have the breadth of bonding potential that carbon does. Carbon's that magic element. It's the granddaddy of all elements. So,
imagine a planet, and there's things underground, not the Horta from Star Trek, but the idea. Imagine crystalline formations, living crystalline formations molded into the rock, that they're there and that's where they stay. But imagine some kind of life ticking in those crystals running through the ground on another planet.
See, I don't
or on this planet.
I don't discount that possibility. Okay, there could be potential life that is doing that. However, it's limited in its further development by the incapability and tenacity of silicon-based bonds. So I don't believe that life could grow to, say, an intelligent level at a silicon-based level. I think that you could maybe have some form of primitive life based on silicon, and yet we don't have any indication that there is, even on this planet. But it's possible that we could find some type of chemosynthetic process that has silicon as a basis, maybe. But I don't think we're going to see intelligence based on silicon. If we're going to see intelligence, I have a strong prejudice toward carbon. As I said, I'm a carbon bigot.
Donald Kanzer asked a question. Did we receive any radiation from the nova? I would have to say yes. It wasn't very intense. It was 6,500 light years away, and it blew up 1,000 years ago. Something that far away, I mean, a wavefront would have come through when the flash became visible on Earth, but it's so dilute because it's so far away, it wasn't significant to us. I've heard people wonder what if Betelgeuse blows up. Betelgeuse is about 10 times closer than the Crab Nebula is. The energy from the supernova Betelgeuse would be a lot stronger than it was from the Crab, but still, would it really be significant from 650 light years away? Probably not.
I think that at the distance of Betelgeuse, 750 light years approximately, we have very little to worry about. We're not going to get pounded with X-rays. We're not going to get pounded with cosmic rays. We're not going to get pounded with gamma rays. It's too far away. You got to remember that light of all kinds, gamma ray, cosmic ray, X-ray, they all fall off. That is, they reduce in intensity by the square of the distance. So light that's 4 times further away is 16 times fainter. Okay?
Yep.
So that's called the inverse square law. And that's what we, luckily, that's probably why we're here. If there was no inverse square law, it'd be interesting to do a study on what would happen if it was only, if it was less than that, okay, or slightly more than that. How would that bode well for life on Earth if the light was not just fell off by the square of the distance from the sun, but maybe by the cube of the distance from the sun? How would that change life here? Would it have developed? And the answer might be no. So the rules of the universe are set up based on the way in which the universe was formed.
And yet, if we look at the Crab there, it is about 10 times farther away than Betelgeuse.
Mm-hmm.
Say Betelgeuse blew up tomorrow, that the energy from Betelgeuse, if that's 10 times farther away, might be 100 times that comparable than what came from the Crab Nebula.
Yeah.
But in the big picture, though, a while back, and we talked about this, it may have been the Webb. I forget. They detected like a big gamma ray burst from billions of light years away. It was over 1 billion, I believe.
Okay.
And when that hit us here on Earth, they actually detected noticeable changes there were ground currents on inside the Earth.
That's right.
And they also noted atmospheric effects from something over 1 billion light years away exploding.
So you can imagine how intense that was at the source, right? So that's pretty strong. Hello, Connie Weber. Connie Weber says, "Oh, the crab is beautiful and full of color. What causes them? Or is that a dumb question?" Oh, Connie, absolutely not. It's not a dumb question. It's a marvelous question. So don't ever say that. Okay. I'll do this. I mentioned a little bit before, but let's go through it in detail. We see this now. This is the beautiful red area. This is an area in the crab where there's a hydrogen emission, and what's happening in there is right in like this area here. We see some hydrogen emission, and it actually there's a red glow. Then down here we see green. This green is oxygen. All right, that's being given off. All right, it's an oxygen glow caused by oxygen atoms that are, it's called O3. It's a doubly ionized oxygen where 2 electrons spew off the oxygen atom and then recombine. And when they recombine, their light that they give off is in the greenish end of the spectrum predominantly. It goes to other colors, but the predominant one is green. Same with hydrogen. The predominant color is red. Now this could also be neon, and there's lots more elements that are giving off colors in here. So, and it's very, very elaborate. There's an awful lot of color that's being given off in here. One thing I want to point out, though, is this guy right in here. Can you see that little tiny star in there? Okay. That thing right in the middle there, that is called a pulsar. That is the Crab Nebula pulsar. And it is a remnant. It's the remaining remnant of the original star that we call the progenitor. It was the progenitor star to this whole thing, and that star is called a neutron star. All right, and like when a star like the sun uses up its hydrogen, it goes up into a red giant, and it will begin to come down. It'll start to do this what's called a thermal pulse, a TP, a thermal pulse. Okay, and these thermal pulses will puff off the outer layers of a red giant star, making nebulae around them. We see those with the Helix Nebula and the Ring Nebula, the Dumbbell Nebula, and so forth. And those thermal pulses create those kinds of nebulas, and what's left in the middle is a white dwarf star, right? It's a star about the size of the Earth that is actually not doing any fusion, but it's very, very hot, okay? Something in the order of 30,000 Kelvin, and it is actually so hot that most of its energy is being given off in the ultraviolet, and that's enough to ionize gas around that nebula it created and cause it to glow. Well, same thing with a pulsar. The pulsar is actually not a white dwarf star. For bigger stars, they go down, instead of collapsing into white dwarfs, they keep right on going, and they become a neutron star, right? And the neutron star is, as you might guess, made of many neutrons on its surface, effectively. Very, very hot, very, very blue. And what happens is it gives off a lot of ultraviolet energy as well, even more so. And other ends of the radio spectrum, it gives off all kinds of energies. But it's also, in this particular case, spinning very rapidly. And we'll find that with these large stars. When they blow up, they give off a ton of energy. And like an ice skater pulling the arms in, the remaining star begins to spin very rapidly. This star is about the size of Manhattan Island. Yet at 6,000 light years away, you can still see it right there. That's because it's extremely bright for such a small object. And as such, as it spins at the unbelievable rate of 33 times per second. And this is what a neutron star does. They're very, very fast rotating stars, stellar remnants. But that's not the record. The fastest pulsar, fastest neutron star's rotation rate, and again, they're the size of Manhattan Island. Imagine a giant sphere, the size of Manhattan Island, right? That star, the fastest rotator, is rotating over 700 times per second. No lie, 700 times per second. That's crazy. That's crazy. And you say, well, then why doesn't it fly apart? Because it's so dense that gravity holds it together. Hard to believe, but that's what happens. Now, that spin, however, is countermanded a little bit by forces at play in the nebula and around the star. Tiny bits of drag induced on it. So pulsars spin very rapidly at the beginning, and they will eventually slow down. Okay? But that takes billions and billions and billions of years. All right? So, we have these beautiful objects to stare at and say, look at. And these will be there for billions of years, these pulsars. But that's the difference between a regular nebula like a white dwarf creates around a regular star like the sun after it dies, and one of these more massive stars. This is the supernova. And these elements are all getting dispersed back to the interstellar medium, and you're seeing it happen right here. Okay, we did 42 here. We're going to stop here, and I'm going to name this up here. We'll say Crab Nebula, get this named properly. There we are.
I have a target for you.
Alrighty. I know what you're going to say. You're going to say
What?
Boogeyman.
No.
Ah, okay. Well, that's a good one.
Well, we can, sure. Maya Leone asked, do we know where the Medusa star cluster is? I looked it up. There is a Medusa Nebula. It's in Gemini.
All right.
You want to give that a shot real quick?
Sure. How big is it?
Give me just a second.
Okay, I think I saved this, so now I'm gonna make sure I save the exactly a scene object. And I didn't. Now I did. Okay, good. All right. So there's the crab, and hopefully you enjoyed that supernova remnant born out of a cataclysmic explosion. And now we'll just take ourselves back to our beautiful.
It's about 10 by 10 arc minutes, so it's going to be small.
Okay.
It might be worth looking at. Who knows?
Alrighty. So, alright, so what we're going to do is we're going to come back into our stellar cartographic unit. And what are we going to call this?
Medusa?
Oh, I know it's the Medusa Nebula, but does it have a name? Let's see if it knows this. Wow, we have Medusa Nebula. Look at that.
It's a planetary.
Alright. Oh, well, let's check it out. That looks pretty big, actually. That'll be pretty big here.
Okay.
We'll find out. Let's go check it out, guys. Watch the telescope move here. There it goes. Heading over to Gemini. And let's see if the Medusa Nebula shows up.
This will be a new one for us.
It will. It looks like it's right there.
Right?
Yeah, well, if we can see it like this, we're good. Because we're at 300. That's it. Okay, so I'm going to move us down here. If you're noticing this line over here, that's actually a spider web inside the building, incidentally. Yeah, that's the Medusa. Okay, cool. All right, this is going to be fun. I would say this one should start off at 45 seconds at 300. Hey Connie, thank you so much. She says, love this channel. Thank you. That makes me feel good. You know, we spent a lot of time and effort putting together everything you see here. I'm actually in Connecticut, and that telescope is out in Arizona in the desert. So I'm 2,500 miles away from it and running everything from Connecticut. So that's the extra layer of craziness. The other thing is, if you're going to be... Okay, we're getting some wind, I see right there, Daryl. If any of you are going to be at Contact in the Desert in June, or in Roswell at the UFO fair in July, June 30th to July 2nd, I'm going to be doing a SkyTour livestream live evening event there as well. Hello, Prow. How's it going, man? And Bucky Barnburner, what's going on? I saw you earlier and I forgot to say hi. My apologies. And Genghis, how are you? Okay, we're guiding now, so let's take 45 seconds and go to town. Let's live stack this now. This is a new one for us. There's the Crab Nebula that we just saw. I'll zoom in on that one more time. Yeah, it's beautiful. I'm glad it's not this close. That'd be dangerous. Okay, so there we go. Pull out right there, and we'll clear it. That's up on the server right now. Hey, Curtis Horns here. How's it going? That's right. We should meet in Pasadena. I love that. And let's talk about the 12-inch optical tube assembly. Okay. Let's...
12-inch OTA?
Yep. Oh, look at that. Wow. It's got some wind, but we're going to correct for that. Look at that. Oh, beautiful colors. Okay, we're going to clear this. And get one that doesn't have wind problems. See our spider web out there is... It's like our wind vane out there. So we'll see if we're good or not. All right, let's pull this down here.
I sent you a private message. You can answer me later.
Okay.
That is slick looking.
Isn't that nice? That's first time for us. That's beautiful.
Yeah. Thank you, Maya.
Yeah, Maya, thank you. What a good idea.
From here, it looks like a dolphin.
Oh, yeah, it does, doesn't it? Going up in the air.
Yeah, its tail is at the lower right, and that's its head toward the top left.
Yeah, let's color correct, and there we did it. And now let's actually try to bring a little bit more out. What a beautiful object. And we owe this to Maya Leone?
Yes.
Wow, nice. Hey Curtis, thank you. If you're gonna be at Alien Con, I'll be there. As I mentioned earlier, I'm doing 2 panels, and they have me doing a talk as well. First time there. I've never been there before. And
wow,
then,
Curtis, very nice.
Yeah. Oh man, this is really pretty. I want to sharpen this up. Curtis, I haven't looked at that yet. I'm sorry. I'm unable to do that at the moment. I'll check it out after. Thank you. Was that images of the OTA?
Yeah.
Okay.
Very nice, Curtis. Bucky, there is also a star that represents Medusa in the sky. Its name is Algol.
Oh, yeah.
It's in the constellation Perseus. Perseus is holding the Medusa's head in his left hand, and his sword that he took the head off with in his right hand. And Algol is the Medusa's head. Algol means the ghoul. Like a spook or a demon or something.
Now, this
Slick. Can you zoom in on it?
Yeah, I'm gonna in a bit. Not quite yet. I'm gonna just try and darken up the backdrop a little more. We have only 4 stacked, but I'll zoom in to the level that we can do here. And I'm doing it at 300, not 350 on purpose to just try and retain some of the subtlety. Look at that. Wow. I can see that our stars are just a little wind-driven here. I feel like I gotta... That only takes 1 exposure to do that, so I hate to say it, but I'm gonna clear it, and we'll come back here.
Looks like a hot pepper when you zoom in on it.
I know, huh?
That's really something.
All right, well, let's see if this one's better. So... Hello, Julie Guzman. How are you? Nice to see you here. Okay, that's looking better. Now, see, that's what 1 frame looks like. All right. Now, we can kind of mitigate that a little bit because we can come down here and say, well, let's take down that setting to try and get rid of some of the noise. And we can, right? But when you see the second one come in, you'll see a lot of that noise is going to go away. And a lot of this rainbow blotching is now getting eaten away by the overlayment of more good data, right? So we have 5 seconds until you see this now change to a much more viewable image. Here we go. Watch. Boom. Look at that. Now suddenly filaments are visible. Mm-hmm. And that'll get even better as time goes on again. And this time, the stars are a little better looking. And we can actually pull this out a little bit.
That's trippy looking.
It is. It's got some oxygen in it. It's got hydrogen. Yeah, nice. What does it want to do for image processing? Let's find out. Oh, not that far off. Look at that. That's something. Yeah, Medusa Nebula.
Well, thank you, Maya.
Yeah, thank
New
you
one
again,
for
Maya.
me.
That's
New
really
one for
pretty.
everybody, I think.
Yeah, we should call it the Maya Leone Nebula. I mean, if Stellarium can make up its own names, we should too. The M. Leone Nebula. That's really cool. But we don't want you to be associated with Medusa, though, so, you know. Bucky says, as red as Marc makes it. Actually, this is pretty well color corrected right now. Let me do one more color correction to see where it takes it. Okay, so this is color corrected. If you look, you know, it's not up to me. These are the curves right here. And the curves have to be aligned with each other in order to have the proper color rendition, right? So if red was out here, it would look weird. Okay? So it's not. Like, I could actually move the red. Okay? Like if I pull this down. Okay, you see how the red curve is moving to the left? Right? Okay, the red curve moves to the left and everything gets messed up. The white curve represents the blend of all three. Okay? So the blue and the green are pretty much aligned with each other, but if you do color correction now, okay, now you see where they belong, and so the color is more appropriate.
If I were going to quibble, I would say hydrogen is more of a crimson red, and that looks like a scarlet red.
Yeah, I don't know.
It's red.
Yeah, I think that there's probably multiple. There's probably multiple multiple elements that are creating the colors we see, of course.
Oh, absolutely.
I'm
That
wondering.
is trippy looking.
I wonder if this is the white dwarf right here. Can you look that up and find out if that's the white dwarf? Because it may not be. I mean, it literally could be off center. It could be this guy for all we know. The thing is, when we look at these objects, we're seeing them in 3D, time, 3D realistic space time. So this could be a bubble that's been elongated and moved to one side, making it look like it's centered when it's not. Bullwinkle says the Medusa Nebula was discovered in 1955. If you didn't catch it, it may not have been there in this, at this brightness level or what have you, because things like this are changing over time.
It does not say which star. Looking at their image, I would say there are several candidates inside it.
Okay, let me.
They have a very deep exposure from the largest telescope at the Wiki-Art.
Okay.
Bunch of stars inside it.
Yeah, I see them. All right, well, that's okay. It's
I would, well, wait, if you go back to Stellarium there.
Mm-hmm.
Zoom in a little. I think not the brightest star, but if I had to guess,
that one there.
Now that I look at it, I changed my mind. I'm not sure.
Yeah. I think that it's probably that star right there.
That's the one I was thinking. Yes.
I think
the brightest star above it, I don't think so.
See, we got a little wind out there, guys, so it's elongating our star images, unfortunately. So I'm going to clear this again. We're about to get another one. And I just want to get 3 or 4 of these so we can examine them. All right. Yeah, look
really
at that. Look at the wind here. Wind is really bad right at that moment, so that's no good.
Mark, excuse me a moment, please.
Sure. Thank you, Izabela, for putting that up. She puts up the most detailed image ever taken of the Medusa Nebula by the European Southern Observatory. I'm just trying to get a good enough one so that we can go at it with our professional tools, but the wind is blowing a little bit. Okay, then we just need a couple more exposures. There we go. We'll get this. Okay, we'll back out a little bit. Nice. All right. Hey, David, thank you so much. That's very kind, David. Thank you. Okay, so we're looking at the Medusa Nebula. And just to be safe, I'm going to save this. Save it exactly as seen. So we have a intermediate level one that I know is well guided. Okay, waiting a bit. David Galich says, where is the scope coming from on the program on screen? That's this scope right here, David, and it's actually out in the Arizona desert. I'm in Connecticut, so I'm running it from here. And I spent the time with our other friends and cohorts in our organization, Marianne Robb and Tara Diulis, and a bunch of really cool contractors. They spent time helping to put in the observatory, and of course we bought the telescope, we refined it, I installed it with them and got it all aligned and had ready to go, so that we just tell it to go somewhere and point it and bam, and even it'll tell where it knows where it is in the sky. Just by, taking a picture of the sky and matching star patterns. Okay, that's called a plate solve, and it knows how to do that, of course. I say of course, but it took a while to get to all this. Let's zoom in and see if we're still in good shape here. Yeah, see? That's the reason I took that picture before. It's a little bit off. What happens is, around this time of night, the wind picks up a little bit as the evaporative breezes come off the desert, and so we do get this little bit of motion that lasts for a period of time, then it goes away. But we got enough to capture this, so I'm really pleased. All right, this is a nice object to have here. So we'll go back to our 1 second shot here, our 1 second night vision shot. We saved it with had a little bit of noise in it, but that's okay. And let's get rid of that. Let's pull that out of there. Come here, you. Come here. Come on. Yeah, over here. Thank you. David Galich says, I love a star party. This is a star party, all right. We have people from all over the world. People from Chile, Brazil, Mexico, China, actually almost every continent. At some points, we actually have people from all the continents in with us and watching. And they all have their own things to offer. You know, it's pretty cool. Bucky Barnburner appropriately says the processes that form the Medusa Nebula kind of foreshadow the eventual fate of the sun. Yeah, in some ways it does, because the eventual fate of the sun is to, you know, swell into a red giant after it uses up its hydrogen. At some point we'll talk about the evolution of the stars and how that works. But suffice it to say, stars become red giants twice in their lives. Okay, after they use up hydrogen, they become a red giant. Okay, and then they start, or at least for our sun, it'll start to fuse helium, all right, into carbon, and that'll be another step in its evolution. Then it'll start to burn and fuse other things, and thus go up another parallel branch to the original red giant branch. That parallel branch called the asymptotic giant branch, or the AGB. And then from there, it'll become, it'll shrink down and become a white dwarf star after it runs out of its last nuclear fuels. So it won't die an explosive death like the Crab Nebula. It'll die a very slow death. And Bulgaria too. Yes, I'm sorry, Izabela. Izabela's in Bulgaria. That's right. So we have a rich assortment of people, rich assortment of cultures, and it's a lot of fun meeting all of them and hanging out with them. All right.
Have we moved on?
No, we're still here at the moment.
Oh. What you doing?
I am just trying to wrest control away here, just to try and get myself back here. I'm waiting for my my control to come back here. I don't know why, but it's not here. Okay, there it comes. Don't know why it took so long. Yeah, exactly. Hello. Sometimes that happens, you know, where the control takes a long time to come. It is 2,500 miles away, so some things do happen. I think now, though, what we'll do is a good thing to try now. Let's go to our 1 second here. Yeah, you can see they move a little bit. I did.
Did
Go ahead.
you lose Starlink?
No, I still have it. We're good. See, I couldn't do anything if I lost it. And we do have Starlink, by the way. So as Daryl just mentioned, we do have Starlink here at the observatory. All right, we're gonna go here. We promised, actually, sort of promised, that we might do the Rosette, but first we're gonna do the Christmas tree cluster because it's right here. All right. So we're going to go there, and then we're going to go to the Rosette. All right, Christmas tree cluster is stunning. Then we're going to, of course, go back to the Comet after we do the next two objects, just to show you the differences and where it is. So Christmas tree cluster, right here. You can see it's sort of a reflection nebula. Then there's another emission nebula down here. It's really beautiful. The emission nebula has a dark nebula within it called the Cone Nebula, which you'll see. So we call it the Christmas tree cluster and the Cone. And it's emission, reflection, and dark nebula. Dark nebula is dust in space. All right. So, first thing we do is we got our guiding going. That's good. Next thing, we're going to take this to, say, we'll do 35 seconds. That's all we need. 35 seconds here. And then go to our stacked image here. And that was a beautiful image that we got.
I was going to ask, did you draw a conclusion or get a consensus on it? I think that's really slick looking.
Yeah, I saved it. Actually, I can save this one again, but I already saved it, but I'll save it again. Yeah. Okay. It's a little blurry, but then I can clear this because now we've got the Christmas tree cluster. Check this out, guys.
That's one to come back to.
Oh, yeah. Ready for this? You ready? Get ready. Boom. Look at this. Look at that beautiful cluster. That is stunning. All right. We've got all this dark nebula up here coursing through the field. We have this feature here. This is called the cone, this little guy right here. And this is the reflection nebula that we're looking at here that is part of this cluster called the Christmas tree cluster. And as we get a few more frames, you'll see that this becomes much more detailed here. This is known as the Phosphor Nebula right here. And we're going to color correct right now and process a little.
When you look at the Christmas tree, folks, it's upside down. The bright star is the base of the tree, and the point of the Christmas tree, the top, is down there by the cone near the bottom of the image.
Yeah, so let's let me see if I can draw that out. So this is the base of the tree down here. And then we have, this is the top of the tree up here. Is that correct? Like that, right?
Yeah.
More or less?
More or less.
All right. See that? Okay, so this is a beautiful location. There's a lot going on in here. And we'll zoom in a little bit because the cone is really exciting to look at too. So you'll start to see now there's some details starting to emerge now in all this. Look at this. There's convolutions and cloudiness and undulations starting to appear in this. And as it gets better, you're going to see some really amazing detail in here. Until then, though, what I'm going to do is I'm going to move this down a little just to reduce some of the noise to help you out. And we'll bring it up as soon as we can. I won't keep it there because it's going to get in the way, but this is the Christmas tree cluster and cone nebula. They're emission, reflection, and dark nebulae. All right, we'll pull that back. All right. Okay. Now let's pull this in. And take us in there. Look at that. And we'll move this in just to intercept more darkness here. Add contrast. Look at that. So now you can start to see that this Phosphor Nebula is a separate set of clouds that overlay this. Isn't that amazing? Here's other dark nebulae in here. This is all dark nebula. This isn't voids in space. This is dark dust. Hello, Lizette Gutierrez. How are you? Oh, we're looking at the Christmas tree cluster. ¿Qué estudiaste para poder entender este tema? So we're looking at the Christmas tree cluster here and the cone nebula down here. This is a dark nebula. So that's what we are looking at right now tonight. We have a little wind out there, which is kind of elongating our lines a little bit. Our starlight, rather, our stars. So, but for the most part, it looks good. Not bad at all. This is gorgeous. We won't do too many of this because we want to go back to the Comet too.
Yeah.
After this, we'll do the Rosette, and then we'll go back to the Comet. Look at that. That's pretty, isn't it?
It is.
Yeah. See, and this looks more like that crimson color you were telling people about for the hydrogen alpha. But again, when it's not as dense, it looks orangey like this, you know? Or when it's brightened. Oh, man, that's pretty.
If I had to guess, I'd say it looks like there's a little too much yellow in it.
Well,
but that's just me.
It is.
Carry on.
It is color corrected. But I will say this: when the moon is up, color correction can have issues. You know, if we reduce the red and the green a little bit, you get this. So you take down the blue a little. And you get like that. So you're kind of back to where you were. What we could do is we could actually, this is what it would look like as a black and white image. Okay. Which is why I didn't get a monochrome camera. I wanted to show colors. But look how much we could punch up the color. And it's interesting because that can help us see these cloud structures, although that's way too vibrant. This is more appropriate right about here. You know? There we go.
Bullwinkle points out that the Christmas tree and the cone were two more discoveries by Sir William Herschel.
Mm-hmm. Thank you, Bullwinkle. You're absolutely correct. All right, let's do one final color correction here.
Herschel really got around.
He did. So did his sister, Claire, right?
Yep. And his son.
Oh. Is that William Herschel Jr. or something? I don't remember his name.
I forget his first name.
All right. Okay, we did 13 frames here. We're going to pause this now and save it. I'm going to name it first. Christmas tree. And there we go. And we'll save it. All right. Save exactly as seen. Now, when we go back to the Comet later, remember those goalpost stars that they're always talking about. We'll see them again, and I'll point them out. All right. And now we're going to go here. And then go here. There's our night vision. Now let's go back. Okay. And then we go to a beautiful heavy hitter, the Rosette Nebula. Telescope won't move that much. You'll see it come down south a little bit. Okay. There it goes. All right, you can already see the nebula surrounding this young hot cluster. And again, this cluster is interesting because what it's done is it's actually cleared a cavity around itself in this nebula and pushed away a lot of the gas and dust in the inner confines where it was formed. And so it's doing what these clusters do when they're young. It's actually basically excavating a hole, a cavity, from its bright and its very, very powerful radiation. All right, so let's bring this over now. Then go down with this a little bit. And then we can start to actually... Okay. move it and center it up here. This is our count here. You watch the count. When the count's moving, it means that we have an active connection. Sometimes our connection is interrupted. Starlink is great, but not perfect. Okay, so this will work. All right. One more jog south. And then we'll catch our guide star. You see it says searching. It's searching for our guide star. Then when it finds a guide star, boom, we're set. And we'll let it start guiding. We'll let it stabilize. And then we will take a 30-second shot. You notice we're only taking shots of a few seconds. The reason is because this telescope is running 25 times faster than it did when we got it. We've added some hardware to it to have it run from an f8 system photographically to an f2 system. The difference is very, very measurable, and we end up getting our speed out of the fact that we're no longer using the entire optical system of the telescope. We're just using effectively the primary mirror and the lens at the opposite end of the telescope, which is up inside here. Our camera is actually on the end of the telescope where the light is coming in. It's really strange. All right, let's do this, and I'll call this one the Rosette because this is what it is. We'll get that taken care of now. There we go. And now let's go and do our live stack, and you'll see the no. Okay, that was the last one. And we're going to clear this. And the first shot you'll see now, and right now, is the Rosette. Ah, look at that. And we'll just show that the way it ought to be shown. Look at that. We're going to zoom out a little bit to capture the whole thing. And this is what I was talking about, the Rosette stars in the middle. This cluster is excavated a cavity in the center of this gas and dust, and that force of that radiation is pushing dust and gas away. So this is in 3 dimensions. It's a 3-dimensional hole around this. Isn't that incredible how that looks? Starlink is already going for a gigabit. There's going to be a gigabit approach that they're going to go into, and as soon as that's available, we're going to probably end up going gigabit. We have a lot of data to send out. There we did. We color corrected. Look at that. Wow. That's pretty, Daryl.
It is.
Ooh, look at that. Beautiful red emission nebula. And we zoom in, you can see some really interesting features. Okay. These dark objects, which will show themselves so much better as we stack a few more, because we're getting rid of the noise, remember. And again, the wind is causing this to kind of dance a little bit.
Still a pretty picture.
Yeah. Uh-oh.
That really jumped there.
Yeah, I think...
I don't think that's wind.
No, that's actually that's actually an artifact of the video. I'm gonna go for better quality. We'll try that. All right. So these objects are gorgeous. These are large scale objects that are several light years long each. Okay. Because this object, like 5,000 light years away or something, isn't it?
Yeah, I don't remember
Yeah.
the number offhand, but it's several times farther away than Orion, which is just to the west.
Yeah. Bucky asked me, "Are you Starlink in Connecticut?" No. Here in Connecticut, I am using Xfinity but I've got the high-end service, so we're actually very fast here as well. It's just beautiful. Very nice. Make a note here.
Everybody's getting faster. I have CenturyLink, and I'm still on a twisted pair.
That's like DSL.
Well, yeah, it's not bad. I'm getting what was it? Nominal 50 megs, and I'm actually getting 68.
Okay.
But now they're pushing everybody to go to fiber optic. They'll give me 4 times the nominal speed for less money.
Wow.
If I go fiber optic.
Well, I have to say, I'm on fiber here. I was the first one in the whole town to go fiber. And the reason was because I had the observatory on the front lawn here, and I needed throughput, you know, and so I ended up working directly with the St. Louis folks doing the fiber, and they used my location as an experiment, and they were here probably 5-6 times adjusting the lines and adjusting the fiber from street to here, from the station to here, to make it optimal. And once they optimized me, they optimized everybody else. So it was great. It was fun to be the first because I got to see it all happen. And I got to learn a lot about them. I had their own phone numbers for all these technicians. It was so cool. You call and you get like a call center in another country. Well, I was calling the St. Louis, calling the St. Louis data center, saying, "Hey, Frank, I got a problem with the. Oh yeah, what do you got? Let me check the measurement. Let me look on. Oh yeah, I see the problem. You know, that kind of. I mean, I got spoiled by that kind of service, man. But they can't be like, they can't be like that for me all the time, obviously. JSCO 77, it's so nice to see you. We are well. Look at this. Look at now. You see the detail coming in here? Isn't that stunning?
Yeah.
Wow. Oh. Oh yeah. Here, why don't we let's get rid of this for a minute. Go full screen. All right, there we go. And let's move this down. All right, and now let's zoom in now a little bit. Wow. Look at that. I feel like I'm in it. Is this too pretentious? Really cool.
Lucky asks, what is the bandwidth of your camera?
I mean, like the color response?
I have no idea what he means.
All right. Well, in terms of the bandwidth, then I would have to say that this is the ASI 294 MC Pro, and you can look up the color curves to see the exact response. But it peaks. It's mostly visible light, okay, but it does peek into some of the other realms as well, slightly, not much. The camera does not have an IR cut filter, infrared cut filter, or UV filter. I talked to a technician about that the other day. So it's actually just a camera that has, it's a straight pass into the sensor, which is sensitive to the light that comes in. And as far as what kind of light gets to it, we're somewhat limited. We don't get a lot of infrared at all because infrared is nicely blocked by our atmosphere pretty well. That's why infrared telescopes are usually high up on mountains. And UV, we could see a little UV. I mean, but as far as, you know, how much quality UV, not going to be much. Again, you're limited by the glass. You're limited by the location, the sensor. But it's, as you can see, it doesn't seem to be a big problem, does it? We're getting these gorgeous images. Let me bring up this and see if we can process a little more out of this. Oh, look at that. Wow.
There's one cloud in particular over on the right-hand side. It's right about 3 o'clock.
This one?
From the center of the cluster, just below that.
This one?
That very red spot.
Oh, right here?
That one.
Oh, yeah.
Could you possibly zoom in on that area a little bit?
Yeah, if you notice, we got one here. There's one up there. There's a number of very red areas, you know. But okay, let's see that too. We've done 19 here of these stacked images. Okay, well, there we go. And you can see a little bit of the drifting caused by the wind. Sorry.
Yes. Yes.
Okay.
Well, this is a cool looking area, though.
Yeah.
Bucky says, I guess he means, what's the downlink speed of the USB connection to the computer?
Oh, okay. I'm using USB 3.2 out there, so whatever that supports, the camera can feed that. Okay, it's actually it's quite fast. You know, you notice when the image comes in, it just comes in instantly. You don't have to wait for the bands to come in, but they're coming in as bands, but you can't see it because the feed it's actually quite fast. I don't know the exact speed. All right, let me. So I'm sorry about that, Bucky. I misinterpreted your question there. Okay, let's bring the computer or the telescope back here for a second. I want to. There you go. Okay. All right.
Seems like there's always more to find in there.
There is.
Such a rich area.
It is indeed. All right. Wow. All righty. All right. What we're gonna do now is we're gonna save this as it is anyway. It's saved as a Rosette. It'll appear on the directory that way. It will save exactly as seen. So you're gonna get that ping file right there. And what does that look like? Well, this is the file that's up on the server right now. You'll see it in a sec. There it is. So you're free to check it out, zoom in on it, look at different areas, and see what's going on. And you can see that there's a little bit of shift, which I don't like, but that's what it is. I'm going to try something while we're here. All right. First things first, let's go back to our night vision mode. Okay. Oh, that's pretty. So that tells you what's really there. All right. So this is our 1 second shot. Look at that. That's really pretty, actually. Holy cow. All right. I'm going to save that too. Why? I don't know. So we'll have two rosettes up there like this. But that's really neat because the extra detail might be important at some point. All right. Okay. Now we'll come out and go into our night vision mode here. Not yet, I guess. Just a minute. Okay, that should be it. All right. And now pop it up. All right. Let's bring back this guy. Computer, and now I'm going to do something else. All right.
Bucky has yet another question for you.
Sure. Are you able to read it for me? So, because I'm in the middle of trying something.
Yeah, sorry. USB 3.1 Gen 1 supports speeds of up to 5 gigabits a second, but that doesn't mean the camera spews that out.
That's correct. There is a speed on the camera that I don't know.
Fast enough.
It wasn't important in the remote setup. I'm waiting here to get to my system. All right.
It's quiet.
I'm waiting for it to connect.
Too quiet.
Why do you say that?
It's a line from an old movie.
Oh.
Or a comedy album, sorry.
I don't understand why we're having to wait so long.
Yacho. You all want to suck it a little while, you so spot. Sorry.
I don't know the movie.
It wasn't a movie. It was a comedy album. It was a play on a.
Oh.
I think a Korean War movie.
Okay.
You ever heard of the Fire Sign Theater?
Oh yeah.
Yeah, it was Fire Sign Theater.
Okay.
I forget which one.
Hmm.
Have you ever heard Everything You Know Is Wrong by Fire Sign Theater?
No.
Oh, that would be the perfect one for you. It's all about UFOs.
Okay.
It's funny. It's a guy with a kook radio show talking about UFOs and aliens among us and all this stuff. It's a really funny album.
Okay.
Everything You Know Is Wrong. Give it a listen sometime. It's a hilarious album.
Okay.
It looks like a big fried egg.
Don't know it.
You will.
Okay. I'm waiting to. There's like a delay issue right now that I'm just working through. Jesus. Okay, bear with us, folks, while we're waiting. It's a issue with the. See, I did that thing literally over a minute and a half ago. So we are in an area or at a time where it's high demand, I think, on Starlink out there. It's 10 o'clock out there. So we're not able to have an immediate response here, which really infuriates me.
Donald Cundler says the Firesign Theater made a cheap video of everything you know is wrong. It's on YouTube.
Okay.
I'll have to look that up.
Cool. 1 second. I'm going to reconnect here. All right. I have another idea. Another idea. All right. Alrighty, that worked. Okay, so at least it appeared to. So now what I'm going to do is check some settings and make sure that the settings are good. And it looks like alright, I had some fundamental settings that were off a bit, and that is kind of what I recognized. And that's good. So now this will be much better for us. Okay, so this is going to go to here, to 20. Boom. Okay. Now we can go back to our status. All right. Now let's go from the Rosette. We're heading over now to. Well, I mean, should we look at the comet right now?
Sure.
All right. Let's do a go-to. That's the coordinates of the comet a while ago. We know it's more south, so the telescope's going to head way up in the sky and head over to the comet. But as it does that, you look where it's pointing, right? It's going way, way up. It will eventually refresh. I don't know why this isn't. It should be refreshing. It's not really there. I'll turn it off and on. It'll be back. All right. Do it again. Let's hold on. Alright, I'm going to start it over.
Alright.
Yeah, that's alright. Start it again. I don't know why it did that, but it did it. Uh-oh. That's why the camera disappeared. Let me rescan. Ah, camera's gone. Okay, well, there is a way around it. Alright. Here's the way around it. I'm going to quit this and start it again. And see if it'll come back. If not, I will have to reboot the system. Which is not a big deal if I follow all the same processes. Yeah, not there. Alrighty. Okay, so I will follow my procedure and do what I always do when I need to do that. I'm going to park the scope and
It's all Bucky's fault. Let's blame Bucky.
what for?
I don't know. We need to blame somebody.
Oh, nah.
He was the one asking all the questions about the camera.
That's okay. Alright, so what I'm going to do is basically it's as if I'm closing down. So I'm going to turn off the scope. The scope is off. Now I'm going to close the roof. Alright, I'll disconnect the scope. Why am I doing this? Because I'm going to reboot the system. So to reboot the system, I have to start from scratch. Essentially. Well, you get to see what it's like. And the reboot takes no time at all. It's a very fast system. So I'll close all those windows. And then I can now just reboot. Because they're all closed up. And when I do that, you'll see it say it's going to restart. The dreaded swirly whirly. Yeah, start anyway. There we go.
Donald, do you mean there was another earthquake? They had some huge earthquakes. When was that? Sunday? Saturday night? Sunday our time?
You talking about Turkey?
Yeah.
Oh.
That's terrible.
Yeah.
Killed, last I heard, like 5,000 people.
Wow.
Maybe higher than that now.
That's terrible.
With Turkey and down into northern Syria, it was close to the area there I've talked about with Abu Huraira.
Yeah.
And Göbekli Tepe and all that, and
yeah.
Southern Turkey.
Gotcha. All right. First things first, we're gonna start up the camera and make sure that the camera. Wait a second. What's that? I don't need that. Make sure the camera comes back like it should. Oh, not that. I don't want that. I want this. Alright, we'll start the camera, see if we have the camera back. If we do, we can restart all this. If not, I'm not sure what we'll do. Oh, we got the camera. Okay. Alright, good. So, it got into a funky mode. Alright, so now what we can do is we can start up all of our systems again and get them running.
JSTL asked, what is the image on your desktop?
Which image?
Your desktop image you had up a little while ago.
Oh, I Not sure. I have to go back and look.
Yeah, well, continue what you're doing first.
Yeah, I'm going to focus on getting this up and running so we can look at the comet again.
Oh, yeah.
And then we'll do that, JSCO. Give me just a few seconds. All right. Well, you get to see what I do on a nightly basis when we do this, right? And this comes up like this. Start up the control program at the same time. There it is. We're getting this going and get rid of that. This is the studious music, the music that says we're getting things going. Okay. And no, we need to waste time. We can just open the roof now. Alright, so the roof should be opening. When I move this, you'll see the roof opening. There we go. And we already have stars. Okay, and we'll turn it on. There we go.
Excuse me just a moment, Mark.
I'll be right here. Okay, and I'm gonna just come in here and camera properties. All right, there we go. Oh, Izabela. Izabela said, "Oh, look, an airplane." No. Okay. This is gonna be. All right. We're getting our GPS fix. There we go. That should be pretty quick. Yeah, all done. Okay. So we're good there. And let's see, this guy, connect the scope. And yep. Okay, look, it's coming back. That might be a fighter jet from Luke Air Force Base, actually. Okay, and then we could drop this up. Never say die, guys, let me tell you. You know, we will never say die. Okay, this is coming up now. There we go. And then this is here, and that's going to be there. A little higher there. All right. And we'll get the latest comet coordinates and put them in and go to the comet. All right. So there we are. Alright, and now we should be able to move up. And we are, and we're going to go right to this guy, and I'm going to put in some initial calibrations, which I always do. And that's going to be this and this. Actually, what's interesting is something was causing the system to lag, and I'm not getting that at all now, so this is good. Maybe we picked it up at a better spot. All right, so that's that, and now we're going to get rid of high precision because we don't want the high precision on. That just takes up more time, and we don't need the waypoint stars because the telescope is lined up very well. Okay, so we just drop this down, go a couple ahead, and get to status. There we are. All right, enter that. All right, now we need to go to get our coordinates for the comet. And let's do that. I got them up here, so we're just refreshing now. Okay, 456.27. Okay, so 0456.27. And Yeah, we're used to this kind of stuff happening. Trust me. I used to have when I was working on the parallax program in astronomy, I had a telescope that was like 35, 40 feet long. The whole floor went up and down to meet it, and things would go wrong, you know. All right, so let's go to that now, and we'll bring this up again. There goes the telescope. Up to that.
Chat's just seeing a black screen, Mark.
Oh, they are? Oh. That's weird. That is very interesting. Why is he seeing a black screen? That's odd. Okay, guys. Sorry about that. Let me try and figure out what's going on here.
Huh.
Oh, I know what's wrong.
I see your stellarium.
No, you're seeing the right thing, but they're not,
Yeah.
and I know why. Now they do.
I see Canopus showing in stellarium. I wasn't aware it was visible to you down there.
Yeah, well, you know what? I'm sorry, guys. Now it's visible. My mistake. All right. Next thing I'd have to do is bring this up, and I'm going to reconnect it because, and now you'll see it should be connected now. So when I go up, oh, you should see the comets right there in the center of the view. And so we go up here, and there it is. It's up there. Okay. Thank you guys for bearing with me on that. But we're good now. Okay. Here we are. All right. Well, here we are at the comet again. I'm going to go back to doing a small little jog. There we go. All right. What I could do when I edit this, I could actually remove that whole segment where this happened. Make it like it never happened. The idea is, don't give up. Never surrender. What movie was that from? Remember that? It had Tim Allen in it. Space.
Galaxy Quest?
You got it. All right.
Believe it or not, I never saw that movie.
We're going to do a 25 second. No, I want to see the tail. 45 seconds here. So here's the comet again.
It's green.
It's green. Scotty. Okay.
Actually, that was said in a couple of different movies.
It was?
They said it's green in one of the Pink Panther movies, too.
Really?
Yeah.
Wow, I didn't know that. Okay.
Yeah, Clouseau's sitting at a stoplight, and out of nowhere, a beautiful girl jumps into his car, and she's sitting there smiling at him, and he's looking at her, you know, crazy, and
yeah.
All of a sudden she leans over and she whispers at him, "It's green," and you know, what the heck? She was talking about the stoplight.
Yeah. Okay, there we go. All right. Obviously the moon's up. We got a little glow, but that's fine. We'll color correct for the blue. There we go. Nice. And you'll notice that it's heading basically toward the bottom of the screen, effectively, kind of like at an angle. Very nice, though. You can see the dust tail splaying out behind, and the coma with the cyanogen and carbon molecules. Wow. It's excellent. music for this. Look at that.
Yeah, we don't see the gas tail now. I don't.
Yeah, I think that's probably directly related to the moonlight that's keeping it from us.
Mm-hmm.
I mean, I am doing a 45-second exposure now, not a 90-second exposure. But still. Outrageous. Very nice. I mean, let's go look at the all sky while we're stacking this, and let's just check out the all sky. All sky settings are going to be the same. We're going to get a 15-second exposure here. We're going to go to full screen preview, and you'll see what happens. It'll come up. Let me take the name out of the way. Come here, you. All right, and then this is what we got. So we got a bright moon. North is at the top. South is down below. East is to the left. West is to the right. And there is Orion.
I see another Chinese weather balloon up at the top.
Yeah, that's actually a Chinese bird turd.
Oh.
What's weird is that we just cleaned that. It was just cleaned out there. And after it was cleaned, the day after, the bird said, "Oh, it's clean. Poop on it."
Yeah. I've never seen it look so three-dimensional before.
I know, right? That's the moonlight for you. Okay. Well, there we go. I'm going to save this as it is. Actually, after giving it the name of a comet. I'm going to do it this way. All right, and now we'll save it. And then save it exactly as seen. Color rendering is just a little bit off on this right now because of the disproportionate blue light that we're getting from the moon. So it tends to go in the wrong direction a little bit. So that is close enough. Again, we could see it in black and white, but that's not exciting. We could also see it gaudy, and that's not terribly exciting. But right about here is right.
I'm sorry, Izabela, I missed your question the first time. The dust tail is curved. The ion tail, which we presently can't see, is straight. The ion tail is pushed directly away from the sun by the solar wind, the pressure of sunlight and stuff. The dust tail is curved because it's sort of leaving a record of itself out in space of where it was.
Yeah.
If that makes sense.
Well, there's another factor too, and that is because the orbit is so large, at any one point, the dust tail should be a straight tail. Okay? Why it's not has to do with the pressure of the sunlight on the dust itself and the stuff that the comet's emanating. So there are a number of factors that go into making that dust tail curve, and one of them is the pressure of the sunlight. When the dust tail comes around, you would think it would follow the orbit, but it actually tends to kind of splay out depending on where the sunlight's hitting it. So it might actually splay out a little bit, you know, but that ion tail is always directly pointing away because that is actually a photometric effect that's occurring, a chemical effect that's occurring on the nucleus of the comet in direct response to the incident angle of that sunlight, which is coming directly from the sun. So that always points directly back at the sun with no wavering. The dust tail, on the other hand, can be free to be migrated one way or the other based on the pressure of the solar wind hitting it.
Yeah.
To some extent, actually. Yeah, that's something.
When Hale Bop came through back in March of '97,
Yep.
the dust tail on it was huge. Great big broad fan shape across the sky.
Yeah.
It was the dust tail was bigger than my hand at arm's length, like a big fan across the sky, with the head of the comet at the small end of the fan.
Yeah.
And then the gas tail was distinctly separate from the dust tail.
Yeah, I actually, for me, the comet that really was the best was Comet West. Comet West was visible in the west, actually, during the setting sun, and it was absolutely unbelievable. Absolutely unbelievable.
And Hyakutake, by contrast, was almost all gas tail, ion tail. It was putting out a small dust tail.
Okay.
Sort of resembled the that was what the coma, the comet, or the nucleus too. It looked like a spearhead. And it showed a pronounced anti-tail when it was closest to us, which was from the dust tail. But Hyakutake just looked like a big blue-green spear flying across the sky. It was huge, but it was long and skinny, the gas tail only.
I'm clearing it to get the next shot, and then we'll take images of that. Let's see what else we want to look at while we're doing this. We did the flaming star and the tadpoles. We could actually look at something that's not as affected by the moonlight. And that's going to be back over on the south. First of all, let's go over here. Let's do that. Let's save that so we actually have a record of that one position.
I think it was Simon in chat a little while ago said they can actually see the comet from southern hemisphere now.
Actually, that's probably right near the horizon for some of them. Now that it's in Auriga.
Yeah, heading toward Mars, they would be down in their northern sky, same as if it were way down in our southern sky.
Sure. Okay.
Curtis Hornets, where are you planning on seeing the 2024 solar eclipse?
Well, supposedly we have an expedition planned to New York State, Curtis. So we'll see. We'll see. I'm not sure. I'm not sure when. We're gonna actually go. We're trying to figure out who all's gonna go, how we're gonna meet up, where we're gonna stay, all that stuff. But that's a very good point. Where are we gonna go to actually watch it?
That's up like by Rochester or something.
Yeah, that's right.
And I think it's late in the day there.
Yeah.
I know the comet's path, or excuse me, the eclipse path. After it passes up through around Rochester, New York, it leaves the North American continent right up by Amanda, a little bit northwest of her, Nova Scotia.
Yeah.
And that's going to be, I believe, right at sunset.
Okay.
She's so much farther east. I think that even from New York, it's going to be, probably late in the afternoon.
Mm-hmm.
And when it starts out here, it starts, it crosses the Mexican border down in southern Texas. And it's actually already past its midpoint by the time it crosses into view over southern Texas. It's already past mid-eclipse, I believe. Well, not midpoint of the eclipse, but midpoint in its travel.
Mm-hmm.
It'll still be total. And that's, I want to say late in the morning.
Okay.
In Texas. And then by the time it works its way up to New York, it's going to be late in the afternoon.
All right. These are magnificent objects. They've started wars. They've nearly ended civilizations. And all they are is icy bodies that are being sublimated by the sun.
The skies themselves portend the death of kings.
That's right. Mm-hmm. Would you like to see M46 and that planetary nebula?
Me?
No, the other Daryl on the line with me.
He says yes, I say no.
Okay.
So there, I guess do it anyway. Well, there's tons of cool stuff to look at out there.
I know.
Very rich area of the sky.
Yeah, it is. Okay, this, and we'll be seeing this again as we move toward Mars with the Comet. We'll be seeing that. Okay, so let's do this. Save exactly as seen. All right. Now we'll get out of that and go to the 1 second time frame for doing our night vision shot. Okay. Now we'll come here.
JSCL, I got to see the 2017 eclipse. I wound up north of Scottsbluff, Nebraska, out in the middle of nowhere. And we were almost directly on the center line of the eclipse. It was spectacular. It happened about 11 o'clock in the morning from up there. And it did cool off. You could feel it instantly when the sun went into shadow.
Yeah, you didn't have any radiant energy on you.
Yep. And that's the wildest thing I've ever seen.
You didn't see eclipse bands.
No, I didn't.
Eclipse bands are pretty wild.
Yeah, well, I was looking for all the phenomena coming and going, and
yeah.
No, I didn't see any eclipse bands. I saw all of totality, though.
Okay.
Totality was like 2.5 minutes long in Nebraska.
Okay.
And I was busy looking.
So this is M46 here and Measure 47. These are two clusters kind of near each other in the sky. Why am I showing them to you? Because they're interesting clusters, and I'm going to show you something with just a, I think 15 seconds is all I'm going to need on this. And I will show you a fascinating and interesting illusion. So let's bring back our live stack and clear it, because that's up there. And there we go. And now, what do we got? Well, we have this. Okay, and we'll let this come in. You'll see this is a young cluster of stars. And in this young cluster of stars, we have what appears to be a dying star. And that's what we see right here. Okay, this dying star is actually a planetary nebula. Oh, sorry. There we go. Right. And you can actually see the white dwarf in the middle of that. But wait, these clusters are all born around the same time. They're all about the same age. But what are they? These stars are not that old. They're in the prime of their lives, and they are fusing hydrogen into helium primarily. So how could this star evolve so much faster than the rest of them? The answer is that it did not evolve faster than the rest of them. But wait, you'll say, why is it like this then? Well, it goes back to the concept of the 3D universe. This star cluster is around 4,000 light years away. But this guy is actually up here in the foreground, 2,000 light years away, roughly. So it's just seemingly superimposed on the cluster and looks like it's part of it, but it's not. You'd go speeding by this whole planetary and then still have 2,000 more light years to go to get to that cluster. Isn't that cool? So this is Measure 46. All right, and it's an open cluster with an apparent planetary nebula, which is what we call that. So that's what it is. Tricky universe, Izabela says. Not bad. So as it goes on a little bit longer, you can see we can start to see some detail in here. This is why I only did 15 seconds, because at 15 seconds, you know, this planetary nebula shows all the detail we want to see. Look at this notch up there, Daryl. See, it looks like it's a darker green. Yeah.
Very distinct.
Yeah.
And the star, the white dwarf, which I assume is at the center.
Yes, it is.
Looks like it's not quite on the center. There's a little dark, like part of a donut hole just to the left of that star. See that?
I do. This black cavity that you see around the star, those are interesting because what that signifies is the detachment of the outer star's envelope at the inner border that's now moving away from the star. And that happens with these planetary nebulae at a certain phase in their lives. The white dwarf is indeed powerful, has ultraviolet stellar winds, okay? But it's not fusing anything anymore. It's just hot. So it's ionizing radiation. It's ionizing with the ultraviolet. But it's not spewing the same protons and electrons off that it was when it was a star. It's just spewing ultraviolet radiation, which is just radiation. It's rays, it's light. It's not particles, right? So that cavity that you see was created at the point where the core began to shrink down and the outer envelope started to move outward during this process as it got hotter and started pushing out, okay, before it became a white dwarf. And so it literally detached the whole envelope, the whole meat of the star from the center core area. And that's why we see these holes in some planetary nebulae like this, and many planetary nebulae like this. All right. So that's an interesting finding with planetary nebulae. But this lies hidden in the sky, and nobody might end up seeing it if not for someone who's going digging around in this constellation. So it's actually kind of cool. And that constellation here, this is Puppis. That's the poop deck, isn't it?
It is.
Okay.
Puppis the poop. That's the raised deck on the back of the ship, you know, where the captain lives under the poop deck.
That's it right there.
Yep. And the poop, Carina the keel, and Vela the sail make up the old constellation called Argo Navis, which was the ship that Jason and the Argonauts took to go get the Golden Fleece.
Interesting. Okay, so we're going to save this after those right there. That's more than enough. Save exactly as seen. All right. And let's go back to this and see if there's anything else we want to see while we're here. There always is something else to see.
For Comet.
Well, yeah, with the moon, I'm not sure that it'll look so hot. We'll go back to that when it's moon-free. Not
M41.
Oh, yeah, we've got M41, yeah, the little Beehive, right?
Yep, right there under Sirius.
Yeah, so let's check that out. That's another cluster that's really cool. First things first, let's get out of this and do what I said we always do. We go into our night vision mode. Okay. And then come back here and head on off to that. So here we go. There it is. For a moment there, you saw the colors. That's kind of cool. Okay, let's head east a little bit. Okay. And we'll let our guide stars kick in, and then we will do what we gotta do. Let's first of all, let's go out to almost the, yeah, there we go. All right, we're guiding now, so let's do 20-second exposure here and come off of our night vision mode and go into our stack mode and clear the last stack with M46 in it. There it is, M47. All right, those will be up there on the server in just a short time. Kathy, good to see you. Thank you for coming. Very nice to see you. And there is the beautiful Measure 41.
Barbarina's wiki in chat says that she is the daughter of Fritz Zwicky, Caltech's first astrophysicist.
Well, Barbarina's wiki, it's so nice to welcome you to SkyTour Livestream. And Fritz Zwicky is someone that I studied when I got my degree in astronomy, actually. And the comet that we looked at earlier was, of course, found by the Zwicky Transient Facility on Palomar. Fantastic. Well, it's nice to see you. Thank you for coming, and I hope you'll become a long-time viewer of SkyTour Livestream. Barbarina, did you see the comet yet? We'll be going back to it one more time before we quit tonight.
You know, she's been here for a while, actually.
Okay. darken this up. Oh, look at that jewel box. Isn't that gorgeous?
It is.
Yeah.
I think I've remarked on this before, but it's interesting seeing Messier 41 here. Reminds me of the left-hand cluster in the double cluster, where you have a smattering of red giants spread out amongst the white stars.
If those are red giants, they probably are.
Yeah.
Very nice.
And we confirmed in the case of the double cluster that the red giant stars are thought to be members of the cluster.
Yep.
They may be some of the first stars to start turning red.
Yeah, it was one of those older clusters. Look at that. How pretty.
I guess I could do a check real quick for M41.
Yeah. Not a bad fit there, you know. Let me just do one thing here. All right, there we go. I wanted to point out we've got that one right there. We've got this one right here. That one right there. Smattering of some smaller ones. Oops, we're black again. Hold on, sorry. That's weird why that does that. Okay. All right, thank you. All right. So as I said, so we got this guy here. We got those. We got this one, that one, and several really small red ones over here. We have a large one there, which may or may not be associated. We got another one up there that may or may not be associated. But that's pretty cool.
I think the article says that they are associated.
Okay.
And the one big red one there in the middle, they're, what did they say again? K3 stars.
Okay, yeah, that makes sense.
The brightest of which is spectral type K3.
Yeah.
Near the center.
K3-3? K numeral 3, Roman numeral 3?
Just K3.
Okay. Barbarina says, thank you for the kind words. I've enjoyed the live stream very much and the professional presentation disseminating important information to the public gave. Oh, thank you so much. It's our passion, right? I mean, this is a remote observatory, you know, that's out in the Arizona desert. I'm in Connecticut. I'm running it from here. Set it up out there to specifically, specifically cater to doing astronomy outreach. So, that's what we do,
Interestingly, they quote a note on visual observation of M41. They say, through the eyepiece, curved lines of stars really stand out, but when you take a picture of it, they tend to flatten out.
Well, let's try something.
But they said they really stand out visually.
Oh, let's see if this is M41 you're talking about?
Yeah.
All right, well, let's do this. Let's
I mean, I see some right now.
Yeah, I'm dropping down I'm dropping this down.
Yeah.
So we can actually use the dynamic range to see what you might see in the eyepiece.
There's like a curved cup of them on the upper left, and the top of the cup is pointing to the upper left.
That?
No, a little bit to the lower right.
Oh, this here?
There's a curved row. Yeah, right there. It's that strong curved row.
Okay. There's one right here, too.
Uh-huh.
There's one right here, too. Yep.
They do kind of show up.
Yeah, they do. But only, when we do this, though, they're kind of lost.
Yep.
We have to actually use the dynamic range here to do that, right? So that we do that, that makes it work better for us. So, okay, neat though.
Yeah, Bullwinkle also says that, who was it? Aristotle may have known about the beehive, the little beehive in 325 BC. One of those objects that
Yeah.
the ancients knew, like the big beehive in the constellation Cancer.
Mm-hmm.
Praesepe, the ancients knew about it, and
Yeah.
there are actually quite a few other deep sky objects that the ancients were aware of.
Yeah. Simon Thompson, the screen time that you're seeing right here, okay, that's the time here in Connecticut. That's Eastern time, okay? So that's my local time. The time at the observatory is 2 hours before that, so it's actually 11:04 at the observatory right now. Okay, this is good. We're going to save this. Save exactly as seen. All right, we'll come out of this.
So Marc's on City Slicker time,
City Slicker
And-
time.
Arizona, and me in Colorado, we're on Yeehaw time, mountain time zone.
Well, honestly, to be fully honest with you about this, not that I would lie, I don't know whether you want to call it City Slicker time or what, but I just think that we're East Coast time is, the same time as in New York City, which I can't stand. I don't like going to cities. For obvious reasons, right? Because these cities are not conducive to beautiful stars,
I don't blame you. I feel the same way.
Yeah.
I remember when I first came to Colorado, I was living up in the mountains.
Yeah.
And I used to stop at a place in Frisco, Colorado,
Okay.
called the Antlers Trading Post to gas up.
All right.
And I'd go there at night sometimes, and I could look east over Dillon Reservoir, Lake Dillon,
Uh-huh.
and I could see the sky glow of Denver,
Yeah.
like an hour and a half away by car.
Yeah.
And you go up there nowadays, and you can't see the sky glow over Denver anymore. You know why?
Because it's lost in the other sky glow.
It's lost in the sky glow at Frisco, Colorado, and in Summit County.
Yeah. I could have guessed. All right, off we're going now to the nebula that is on this glass, the Seagull Nebula. The Seagull Nebula is just beautiful. It comes out beautiful on our SkyTour LiveStream flask here, or our travel mug. Calling it a flask is kind of gives it the wrong connotation because I don't drink. All right. Yeah, I don't quite know where the. Oh, actually, I probably could figure it out if I increase my gain here.
What about on special occasions?
No, I don't. It just doesn't taste good to me. There it is. Doesn't taste good to me. It never has. I've never been one of those people that likes to drink. I just don't. Don't know why, but not me. Okay, let's do this. Let's go to the east.
I had a drink at New Year's.
Yeah, I didn't. I was just like, whatever.
Celebratory drink.
Yeah.
Actually, I quit drinking for 30 years or more. And some years back, I decided to allow myself one medicinal vodka or brandy a day before dinner.
One medicinal. I didn't know that was medicinal, but I guess I've heard that
Oh
before.
yeah. one short brandy.
Yep.
And for vodka in the summertime, usually brandy though. And, it's a little short one, and you know, you don't know what to believe anymore. One day they'll say a drink a day is good for you, and then they'll say any alcohol at all is bad for you. They seem to be swinging that way again lately.
Yeah, I don't know. I don't know. It just never tasted good to me. You can imagine how much trouble I had in high school, for instance. You know, I wasn't the guy that would party with everybody else. I was like the guy that was a designated driver, you know. Mark, you gotta go with us. Why? Because we're gonna be getting drunk and you gotta drive us. Okay. That's how it was. Okay, let's pull this in and go south now a little bit. Don't have to go much.
Sam says you weren't drinking the right stuff.
Well, I don't think anyone wants to hear this, but I will tell you. I have, to date, in my life, never been drunk once. Okay, I know, nerd, geek, whatever, but I haven't. All right.
Let me ask you an important question then.
Yes.
Do you ever wear a necktie when you don't need to?
A necktie when I don't need to, as in, I mean a necktie, like a tie.
Yeah, a necktie.
Like when I don't need to.
A cravat, a necktie.
Okay.
Even a bow tie, I guess.
When I don't need to.
When you don't need to.
No, that I can't say. I tend to be a little more casual. I wear ties at funerals and weddings.
Yep. Okay.
Or when I'm doing talks, I have to admit, I'll wear a black suit with a cyan-colored necktie. You know, and that's really, or white. You know, that looks nice. So.
You should try wearing turtlenecks.
Oh, I have, but not with ties.
Not with a tie, no. But yeah. I mean,
a sport
jacket.
Nice yeah, turtleneck with a sport
jacket.
Yeah, I do that.
A good-looking turtleneck that makes you look. Gives you that professorial look, you know.
Oh well, it's not like the look I need, right? I mean, that's not what it is. But I guess I get your point. You know. But yeah, I'm not looking for a specific look. You know, I am what I am. Okay, we're gonna start this now. Yeah.
Oh, I am what I am, Brutus.
Oh, you had to say it, didn't you? Okay, we're gonna do a 40-second shot here of this. We're guiding fine now. This is the Seagull Nebula, a distant stellar nursery that has copious amounts of dark nebula in it. This dark dust is my hot button. I've told you this before. You know, it's within that dark dust from which life springs in the universe and from which stars are born. And that dust has hydrogen in it. It has ammonia ices, water ices, carbon dioxide ices, and lots of other ices. And when those are sublimated off with the formation of a star, you now have this soup of material. All right? That soup of material is what is actually, look at that. This soup of material is what's actually the precursor to planets around that protostar, that star that's forming in that region. So the dark nebula itself are these small dust grains. Those dust grains connect with each other and bond with each other and make larger dust grains. And They're made of silicon, they're made of carbon. But remember, supernovae spew so much material out into the universe that all these other elements are spewed out too. Elements that make up you. All right? Everything in you has been created in the heart of a star. Other than possibly hydrogen that might have been around since the very Big Bang. You might actually have primordial hydrogen in you that was formed 13.8 billion years ago. You know, isn't that amazing? And you might also have material in you that makes up your bones and other parts of you that was only maybe 11 million years old, depending on when the star went supernova that caused it. But it was probably billions. Because you were born now, so the Earth was made 4.6 billion years ago. So, what I was saying was, when the Earth was born, when the Earth was born, the star that created all the material might only have gone supernova several tens of millions of years before that. And then that material mixed with our solar nebula and formed this rich assortment of materials from which the planets were made. Beautiful, extensive nebula, many light years across. Let's see if we can add some detail to it, shall we? I think we can. First of all, I'll do another color correction. Slight change in the curves. I will darken up the background. Okay, and now we'll bring this back a little bit. This is called a push when you move this mid-level toward the peak of the curves. And this is called adjusting the black point. When I do this, look at that. Wow.
Izabela, I may have misspoken a bit. Fritz Zwicky was born in Bulgaria. He's of Swiss citizenship. I guess they call him Swiss. And he goes way back, 1920s, 100 years ago.
Yeah. It does look like a parrot, Donald Kunzer. Yes, I agree. Looks like a parrot with its beak.
I've said that before, too.
Yeah. Yes, ask Barbarina if she's still here. Wow, that's pretty. Okay, the color correction adds a little more red in there. That's pretty. Oh, yeah.
Barbarina is mentioned in the wiki article on Fritz Zwicky.
That's good.
Don't want to get too personal.
Well, it's in the article. It's David Galich, yeah, the primordial soup. That's what we're talking about when you mentioned that comment before. Sorry. Simon says, that cobweb is distracting. It is. We can actually move it out of the field. There. So now you won't see it anymore. There you go.
Zwicky, along with Walter Baade, promoted the use of the first Schmidt telescopes used in a mountaintop observatory in 1935.
I think the 48-inch Schmidt was something that he had done, because I think because the telescope now it's called I think it's the same scope called the Ocean telescope. And I think that's what the Zwicky transient facility is now built upon. I could be wrong about that.
I know what you're talking about.
I think that might be true. It could be wrong. Let's zoom in. Let's see what we're looking at here. Again,
in 1934, he and Baade coined the term supernova.
Very cool.
Somebody in chat mentioned that, and I had to look it up. 1934.
Well,
Hypothesized that supernovae were the transition of normal stars into neutron stars, as well as the origin of cosmic rays.
Yeah.
He found 120 supernovae.
Wow.
And he did it the old-fashioned way, like we talked about Clyde
Tombaugh,
Pluto. He did
blink
it
comparator.
looking at photographic plates with the human eye.
Blink comparator, yep. I used an old-fashioned blink comparator when I was getting my degree, because we actually had one, and I pulled out some historic glass plates and I put them on there and looked at them. I could tell you, you come away from there going like, your eyes are like playing tricks on you, because you're just swapping back and forth. So it's like you're almost generating like an epileptic seizure when you're going back and forth so fast with it. I'm not epileptic, but that was weird, because it actually made me kind of feel how that could happen. I could understand it, in other words. This is pretty.
I know what you mean.
That's really pretty. Really pretty. Wow. Okay, I'm going to save this here. But after I call it a name here, we can, there we go, Seagull Nebula. Okay, and save it exactly as seen. All right. Okay, we'll clear it. Seagull Nebula was pretty, there's no doubt about it. But we'll be going to something else here now. And I think I ought to get some sleep. So what I'll do is I will take us to, one last time, I'll take us to the Comet. What do you think?
Okay.
Why not?
Sure.
Watch the telescope now over my head. It's going to go zipping up. Okay. Okay, stack is reset. There. As you can see, the comet is way over there now. There it is. There we go. There goes a satellite. Right up there. Alright, let's go south a bit. Alright, just a moment while we wait for our satellite internet service to come back. There we go. Now we're gonna go east a bit. That's still going south. Now we're gonna go east. Comet's looking very interesting. You can see how different it is, how the location is so very different. Ay, ay, ay. Come on. Stop doing this to me. Alright, we'll get it over there. Okay, so that looks good. So let's go and let's do 25 seconds on it right here. All right. Now let's see where this puts us. Okay, now that's an unprocessed shot. If you look down here, you can see the curves are way to the left here. Okay, so there's the peak of the curve. So we're way off. So if we actually brought this curve in manually, okay, you'll see how much more of the comet becomes apparent as soon as we hit this location right here. And you'll also notice that the telescope is leaning way over. So it's looking into the north west right now. All right, but you see how the shape of the dust tail has changed since we first looked at it.
Mark, Izabela has a pretty heavy question for you.
Okay. Hey, John Proctor, how you doing?
We were talking about Zwicky's beliefs and stuff that was touched on in the article.
Yeah.
At Wiki. She read it, I read it, some others read it evidently. She says, Mark, do you also believe that the universe could be an intelligent creation?
Interesting concept. I don't have any opinion one way or the other on that at the moment. I don't thwart anyone from thinking that. I don't. On the other hand, I also don't encourage it. So I'm kind of neutral on it. I'm ambivalent. It almost doesn't matter to me, which is kind of interesting. But that is an interesting question, whether it's an intelligent creation or not. Because then
I'm sorry, go ahead.
Because then you have to say, okay, if it's intelligent, then what created it? And your first thought might be, well, is this where religion comes from? Do we call it a god? Well, any technology sufficiently advanced will appear as magic or godliness to another civilization. So could it have been a highly advanced species which made this playground that we call the universe? We can't say no. We can't say no to that. But the question becomes one of capability and motivation. Would they do that? I don't know.
Albert Einstein supposedly said that my sense of God is my sense of wonder at the universe.
Yeah.
And maybe best just to leave it there.
Yeah.
Somebody else said, and I'm paraphrasing, I don't remember who said it, but it would be a shame for this great big universe to exist and there not be anybody to enjoy it.
Yeah, I understand that. All right, so obviously, oh, we got Centaur Flyer. How you doing? Nice to see you. Thanks for dropping by. Again, as far as the universe goes, I mean, it's enough that the universe is there, and I don't try to assign any kind of creationist theory to it. And I think it's human nature to try and say, well, if it started, something had to start it. What's that something? What's that something, a being? It's like, we'll never know that. And I don't try to wonder about it because it is what it is, right? And Simon Thompson says it well. Science and religion do not go hand in hand, and they don't. They should be kept separate. Could science someday explain religion? Maybe so. Could religion explain science? I don't think so. So I don't think it's a two-way street on that. That's just me.
How does the anthropic principle fit into all this?
Well, I mean, you mean the fact that humans are here at all?
Well, how does it go? The universe seems like it's almost designed for life or for people, or...
Well, see, I don't actually feel that way. I'll tell you why. How many of you have friends that have skin cancer? How many of you have friends who died in an earthquake or a tornado or a hurricane? The Earth is not well suited to human life. We survive in spite of the Earth, okay, which is apparently always trying to kill us, okay? And the universe is always trying to kill us too. We're but beneath this narrow, this really thin shell of atmosphere on this planet. So we survive in spite of the universe. I would like to say we survive because of the universe, and we do to some extent. But the sun is not the best star to have for a planet with our kind of life. We're soft, we're pink. We have diseases born of solar energy and electrical energy and so forth. And radioactivity that's in the core of the Earth. You know, all of these things conspire to kill us. And there we go, still surviving in spite of it all. So I'm not really convinced. I think that mostly it's more like we're surviving in spite of the universe. It wasn't designed for humans, I don't think. I think that we're surviving in spite of it. Because it doesn't have the best qualities for humans on this particular planet, in this particular solar system. I mean, let's be clear. We were struck by an asteroid, not once, but many times. One we know of very well, of course, was the KT boundary event, right? Which is, of course, the death of the dinosaurs. So we know that there's others. We wouldn't have a sentry list where we're looking at asteroids and figuring out their coordinates if we thought that we were going to survive, you know, without any question, because it's not true. You know, we are here at the, you know, and subject to the laws of the universe, and sometimes those laws are just not conducive to life as we know it. So that's my feeling on it. You know?
Well,
Simon Thompson says the sun gives us life, yet it tries to kill us at the same time. Yes, that's true. We will be killed by the sun eventually. Everybody on this planet will not get off of the planet when the sun stops functioning the way it is now. So there will be life taken by the star.
Well, I think we're straying into philosophy instead of science, but you know, it's interesting.
Well, that was
interesting
actually
to contemplate.
It is, but that's actually factual, right? I mean, it's not philosophy. The sun is spewing rays that kill us, that causes cancer. The earthquakes do happen, which take lives. Tornadoes and hurricanes kill people. Tsunamis kill hundreds of thousands of people at a clip. So the planet is not the best type of planet that is most conducive to our kind of life. And those are factual reasonings, not philosophical reasonings. If you want to go down the philosophical path, you can say, well, you know, is the way that the human race interacts with each other something that is conducive to continuance? You know, well, maybe not. I mean, if you go to Easter Island and you look at what Easter Island looks like now, the Rapa Nui as the inhabitants, right? They made the Moai statues as for reasons really kind of mysterious. I mean, they're lined up on pedestals looking out in the ocean. Are they supplicating the gods to save them at a time when they thought their civilization was coming to an end, which it was and which it did? I mean, that's a philosophical question, right? You know, how did that happen? There might be factual data in there to buttress up a philosophical argument, but those Moai statues are a perfect example of a civilization in decline. In the same way that you think of, and this is more philosophy, in the same way that you think of Easter Island as being isolated, you know, all those miles from Chile, which is where a lot of the people ended up going to eventually. You have to understand too, and you do, that Easter Island is a metaphor for the entire planet Earth. Okay, they used up their resources. They fought amongst each other. They had diseases run rampant within their communities, which decimated the population. And so that's Easter Island, right? And
I think you're looking at too small a scale.
Well,
if you just look at planet Earth, I mean, they're talking about the universe.
Yeah, but it starts small, right? It starts small. So you take Easter Island and use that as a metaphor for the Earth. You use the Earth, use it as a metaphor for the local group and our solar neighborhood, actually. You know, so we could do that once we knew something more about it, but we don't. We don't know more about the universe and our local group. We don't know more about any life that may be existent elsewhere. We don't have any idea. Not yet. That's interesting right there.
Is that saturation or?
It's a odd color modeling from possibly saturation, but it implies a shadow of sorts, and it might be just the nature of the coma gases and coma ionization going on. Wow.
As I look at that, as it's sitting right there now,
Yeah.
that scale, I mean, I see a bright spot above the center of the coma
Oh, I see that.
and a little dark spot under. Well, the dark spot is what you were remarking
Yeah,
on.
let me just try and make this stop. You're talking about this right here is the bright spot,
Yes,
and the dark spot is this down here.
yes.
Yeah.
And then it looks almost like kind of curved around on the left, almost like a spiral or a swirl of sorts around that dark spot.
Yeah. Now, see, JSCO just asked an interesting question that, again, borders on philosophy. He said, how do you get something from nothing? Well, that's a cosmology question that is yet to be answered. We don't know. But you know something? I'll tell you right now. You know how you hear that there was this infinitely small primordial superatom which blew up and made the universe, right? Well, guess what? None of us think that the primordial superatom was this infinitely small little thing. It wasn't. It was this massive thing. It was gigantic, and we don't really know much about that era except that we can just guess what was going on then, right? But the primordial superatom certainly wasn't an atom at all, and no one actually, cosmologists, astrophysicists, astronomers, none of us think that. We know that it was a massive object. In the same way, we know that black holes, which they talk about having a singularity at the center, there is no real singularity at the center of a black hole. It's a massive object that swallows up material, and the more mass it swallows up, the larger its radius gets, and the larger that Schwarzschild radius grows, which becomes the event horizon location, right? So that is something that we have to consider, right? Is that black holes, we measure them as if their gravity acts at the center. But that's because that's how our physics works. That's not how it actually is. Okay, I'll give you an example. When you measure the gravitation, I've talked about this before. When you measure the gravitational force between two objects, the calculation is capital G, big M, little m, over r squared, the radius between them. The radius is measured from center to center, all right, of objects. So if you want to measure the gravitational force between the sun and the moon, then that force is equal to G, the gravitational constant, times the mass of the Earth, times the mass of the moon, over the radius squared, which is the distance between those two objects, center to center. So our equations are based on center to center. So when we talk about black holes and Schwarzschild radiuses and all these things, we talk about it as if it's acting from the center, all right? It really is acting from the center, but there's mass around it, and it's not, it's not like we're ignoring that. But in order for the calculations to work, we actually run it. We think about it as if it's working center to center.
Well, we really don't know what's behind the Schwarzschild radius.
Well, actually, there's some good ideas.
By definition, it's undefinable.
Yeah. Barbarina says the 18-inch Schmidt telescope was built by her father, who was Fritz Zwicky. He hand carried the Schmidt lens, optician Bernhard Schmidt, from Germany. The 48-inch Schmidt was renamed, and the ZTF mounted on this instrument. Okay, so see, I had mentioned that the ZTF was mounted on the 48-inch Schmidt, and that is now that new Ocean telescope, I believe, Barbarina. And you can correct me. So I think that's pretty cool. You know? Barbarina, you got to hang out with us more. This is really good. I'm glad that you've joined us. I hope you subscribe. I hope you subscribe, by the way. Because we do real astronomy here. We don't do any of this other stuff. That people say, "Wow, look at that cool thing." It's very interesting. But we also, as you probably have seen, educate people too. And whether they know it or not, they're going to learn something.
Whether they want to or not.
Whether they want to or not. Yeah. By the way, look at this comet now. I had this brightness set like this, and now it's got this strange look to it. This could be an artifact, or it may not be an artifact. It might just be... There might be a change in the brightness of the comet head there. I can think there might be. So let's go here.
Oh, Izabela, that's an interesting point. Did you see the picture, Izabela's treatment of your comet image from last night, Mark?
Yeah, she had that dark spot in it too.
I wonder if that's what we're seeing now.
Well, I do think that there's something real there, and I'm not sure exactly what it is.
That's trippy looking. What if you took another exposure to see if it's still there?
All right, let's do that. I mean, this is blurred a little bit, so let's do it. Donald Kunzer, it's not exposed rock as far as we can tell. I don't believe that's true. Neat idea, but I don't think it's exposed rock. It'd have to be a massive rock, and we know that the comet's probably only a few kilometers across.
Right.
Okay, so this is... We're going to save it just like this, because this is the actual image without streaking on it. Not a lot anyway. So if we zoom in, we'll let another couple come in anyway, but then we'll move this guy down a bit and see what we got. There we go. Okay, so you can see it's really small. So it's possible that we're seeing an artifact, although it does look like there's a little shadow under here. And it's not really a shadow. It's going to be a lower density or something in the nucleus, in the coma. The nucleus is here, Bucky, but it's underneath this coma. The nucleus would not be visible to us. If you took away all this gas and all these ions, you would actually not see anything there. It'd be too small to see. It's only a few kilometers across. So, unfortunately, you wouldn't see it.
Izabela, we noted earlier when Marc first took note of that dark area, was wondering whether it could be an effect of saturated pixels, I guess, or...
Well, and time exposure where it's been blurred and dragged out a little bit.
Yeah.
That's certainly got something to do with it, without a doubt. I'm not sure what, though. Okay.
I mean, we don't see it now, but...
No.
Is this the same exposure or another exposure?
This is 25 seconds. So we saw it in a stack, a 25-second stack.
Yeah.
So we can take this down a notch here. Okay. Interesting. So I have to say, I'm really, really happy that we did this. It's not the last time we're going to stream the Comet. We'll be streaming the Comet again. It's the 8th now, and on the 10th, this Comet will be all the way up by Mars. Okay, so where's that going to be? I'll show you. Let's go to the telescope now. And just go up here. Right up here. Okay, here we go. So we're way over in the west right now. But let's go look at this. So the comet's image is not that good right now because of that. We're only a few degrees above the horizon, but it's moving from where Capella was. It'll be up by Mars. Okay, it's heading this way. All right, and that's south. Okay, when we look at this, this is the upper part of our red square. If we zoom in, you'll see. Okay, you turn your head to the right, and the numbers are upright. So that means that this is the upper left, this is the lower right, etc. So Mars now in this view is going to be basically down below, straight down from this, right from here. So it's actually heading down that way. And it'll be there by the 10th. So it's moving pretty rapidly.
Yeah, but like tonight, I mean, the comet's going to move on to Mars in just a few days, and at the time we start the stream, well, the comet is almost straight overhead.
Right. So we'll see. We'll see Mars by the comet in just a couple of days. It'll be in the same field, so we'll be able to photograph it. You get some really cool photographs of it. Hello, PG. I think I said hi to you, Petita. All right. Well, anyway, it is almost 2 a.m. here in Connecticut.
Yep,
and
almost midnight here.
Time for this astronomer to go to bed. But that's okay. I am very pleased you guys could join us. It was wonderful. We had a great time with you. I really appreciate that you came and spent this time with us. We will be doing it again because we always do this again. And keep in mind, go to SkyTourLive.org, and on the upper left, it takes you to this stream here. The upper right, it takes you to the Patreon if you'd like to contribute and be part of our Patreon. We have a number of wonderful Patreon people. We're going to be putting the names up here in the next stream. And so,
I meant to ask you about that.
Yeah,
I'm seeing that more and more now that YouTubers with Patreon, they like run it in credits showing all their Patreon members.
Yeah.
Each stream.
Yeah.
You're gonna start doing that?
Yeah, actually, I have a set of our patrons, okay, which is right there, okay, so far, and we're getting more, hopefully, as time moves on. Don't have a lot yet, but then again, I only started the Patreon like a few weeks ago, right? So we got time. Yeah. We got time. And I'm going to offer, like I said, I've got $5, $10, $100, and $200 tiers, and I'm going to split those up a little bit more, and maybe throw in some stuff like our beautiful mugs and stuff like that for certain tier levels as well. And that's once we have them available and all that. So it's right now, it's all testing, but I do have a really cool pair of sneakers coming that have nebulae on them and our logo. So we can actually get clothing, and Robin Curtis got a blanket, a full-size blanket for like a bed with the Christmas tree nebula on it. It looks stunning. It's like, man, this is just crazy beautiful.
So
Izabela,
stuff now.
Izabela, your name isn't on there yet. That's why I didn't put it up yet. I got to put that up. Okay. Thank you, Barbarina, for coming out and just really homage to Fritz Vicky, your dad, a great astronomer and astrophysicist, and he has and always has had my admiration. So thank you so much. In fact, we did a show about the Zwicky transient facility on our SkyTour radio program, and it was we showed it and talked about it and everything. So it was really wonderful. But thank you very much. Good to see you. Izabela, I'll have your name up on the next one, I promise. All right, folks. It is that time. I hate to say it, but unfortunately, you've heard it before. If you haven't, I'll just say it like this: Trizzle, trazzle, truzzle, throme. Time for this one to come home. Do you remember that?
Help, Mr. Lizard, help.
Help, Mr. Wizard. It's Tutor the Turtle. Tutor the Turtle. Yep. Excellent. All right,
Good night,
guys.
everybody.
Well, you guys have a good night. And, you hear that music. You know what that means. When you hear the music at the beginning, we're starting. When you hear it at the end, we're done. Thanks, David Gallich, so much for that donation. Thank you very much. Helps keep the lights on and the telescope running. All right, guys. Say goodnight to Comet C 2022 E3 ZTF. And we will be back in the next SkyTour live stream. So we'll catch you later.
Good night, all.
Good night.